So these are our co-organizers of the IoT Micro Conference. We have some really interesting speakers this year. We've got Vaishnav Ma, who is with beagleboard.org as well, and he'll be presenting on Microbus. We've got Michael Magyar, who is a former colleague of mine. I'm quite excited for this. He's presenting on Thread and getting IoT applications running with embedded Linux. We have a small break. Then we've got Renode. We've got Michael Gilda from Ant Micro speak about Renode, which I'm quite excited about as well. And then, of course, Stefan Schmidt, who is kind of one of the godfathers of Linux WPAN, presenting on 802.15.4 updates and RPLD updates. And then we've got a break, and then you're all stuck with me for the last presentation. So, yeah, any words, Jason or Drew?
Excited to kick off the second year. Thanks a lot to Christopher for helping be the main organizing force behind this, and I'm excited for the first talk. Definitely, finally have some patches posted in the mailing list, so I think we'll hopefully be able to get some good feedback. And Vaishnav was one of our Google Summer of Code students in the past year, so it's exciting to see one of our GSOC students go on and do upstream development. So that's been great to see.
Yeah, so for me, it's just exciting. You know, we've been working since the last Plumbers, putting different pieces of technology together to try to streamline people's IoT experience. You know, we had a lot of lessons learned last year, and we're going to have a lot more lessons learned after today's micro conference. But it's really nice to see some things starting to come together in the Linux kernel and in Zephyr as well for IoT, and I think that it spells good things for users in the future. And so I'm excited to see some of the folks that are back and folks that are new to hear the updates, because I know there's been a lot of really interesting things to learn about over the last year since we met face to face.
Yeah, so we're going to hand it over to Vaishnav in just a minute. I just wanted to ask all the presenters and co-organizers, after the very last talk, I would really love it if we could do a group photo sort of thing. It'll just be a screenshot, but I'd like to do that every year if we could, just because it's, you know, this is year 2 of our micro conference, so there's a bit of nostalgia. Yeah. In any case, yeah, I'm going to hand it over to Vaishnav, I think, right now, because everybody's probably tired of me going on and on about this sort of stuff. But yeah, it's exciting. I hope you enjoy the micro conference. And here is Vaishnav. Let's see if I can find him in the list here. Make presenter. Okay, there you go, Vaishnav.
Hi, Chris. I cannot select the presentation as the current presentation.
Sorry about that.
From your view.
Yeah, sorry. I have to take presenter again to do that. Let me just do that really quickly. There we go. And I'll have to be downloaded. And there we go. Sorry about that. Thanks very much.
Thank you. So, like, I think I don't have the control to switch over the slides also. Oh, okay, so it's done. Thank you. Hi everyone, I'm Vaishnav, a recent undergraduate student from Kerala, India, and I'm a contributing kernel developer at beagleboard.org. I would like to present and discuss with you today the concept of Microbus driver for add-on boards on Microbus port. Before starting on the details, I would like to thank the organizers of the me and IoT Two micro conference for providing me this wonderful opportunity. I also would like to thank the Microbus Foundation for the constant support and Microelectronica for providing the hardware for testing driver. The Microbus is an add-on board standard from Microelectronica, which anyone following the specifications can use in their board designs to add Microbus sockets and also to develop new add-on boards. There are more than 140 development boards which have incorporated Microbus sockets in their design, and there exists more than 850 Microbus add-on boards, ranging from simple sensor devices to wireless connectivity boards. The socket has standard as 2 rows of 8 pin seats and can support devices that use I2C, SPI, UART, PWM, analog inputs, interrupts, and GPIO peripherals. The standard has some restrictions in the usage of the pins by the device, which helps to create fairly simple device to overlays than for highly flexible add-on board standards like CAPE, HATS, or STEELs. But it is worth mentioning that the Microbus standard is fairly flexible enough, and there are more than 850 add-on boards from over a wide domain. The main point of discussing about Microbus driver in the Linux kernel is that there are more than 150 add-on boards with existing device drivers in the kernel, which we can use with little or no effort. Currently, the most straightforward way of using the device driver support for these add-on boards is through providing suitable device tree fragments at boot time. This method has an issue to maintain a separate device tree overlay fragment for each socket for each of the supported targets running Linux. Thus, having to maintain a large out-of-the-tree database, considering single target of the BeagleBoard or Pocket Beagle, with 2 Microbus boards, we need to maintain about 300 separate device tree overlays for the 150 add-on boards with existing device driver support. Also, this method is time-consuming and error-prone for beginners, and a mistake in the device tree overlay can even prevent the system from booting up. So, like, this is not to point out any disadvantages of the device tree. So, device tree is the most flexible mechanism to describe any device, but the Microbus standard allows us to the restrictions in the standard allows us to fairly describe using a different mechanism also. Adding to this, the device tree maintainer Frank Rowan has a proposal to solve the issue with maintaining separate overlays for devices on standard sockets like Microbus. But for some solutions like adding the Microbus ports dynamically over Graybus, this solution might not work. We'll discuss later about the topic of adding Microbus ports dynamically over Graybus. Before going into the Microbus driver, let me describe a bit about the previous history of trying to add alternative support for Microbus add-ons on Linux targets. Last year in 2019, I was working on a Google Summer of Code project under BeagleBoard.org Foundation under the mentorship of Jason Kreiner, where we tried to solve the problem through the application of Graybus, which was when we realized that Graybus alone cannot solve the problem, since there was no existing mechanism to describe devices on SPI or I2C buses, and we were not able to pass enough information like interrupt, the name properties, name GPIOs to the device driver for a successful probe. Now let us look at the Microbus driver, which enables the Microbus as a probable bus where the kernel or host can discover what device sits on the bus at boot time. This is possible by storing the add-on board information, like the information that is required to be passed to the device driver probe on a non-volatile storage within the add-on board. Currently, for a proof of concept, we are storing the identifier data on an EEPROM that sits on the I2C bus of the Microbus board. The identifier data format we are using is an extended version of the Graybus manifest, which is used within Graybus to describe the capabilities of a module. In the current state, we have tested support for about 111 Microbus add-on boards, and a new Microbus version 3 standard is being developed by Microelectronica, where the add-on boards will have a mechanism of storing the identifier data within itself. So we can see the Microbus driver as a in the block shown below. So the Microbus driver takes in the board specific information from the identifier stored on the add-on board. So for now, it will be an EEPROM on the I2C bus, and then it takes in the device.
I'm just seeing an icon on my screen. I don't know if anyone else is, but it looks like the slides went away.
I'm still seeing the slides.
I can see the slides as well.
Okay. All right. No problem then.
So the
Vaishnav, sorry, I don't know if you are checking out the public chat too, but some people have posted a couple of quick questions. I don't know if you want to address them now, or we could wait till later, or other people could do it in the chat. But it's up to you.
Okay, so Stefan has asked, so dynamically here means at runtime. So like we are not trying to do it at the runtime, so we are trying to do it at the probe time. So like on the physical Microbus ports, it will be at the boot time. So we will be covering the section of adding the Microbus ports dynamically over Graybus. So in that case, we will be discovering the device at the port probe time, like at the point where we add the Microbus port or the Graybus. So as Frank has asked, so the current method of adding an EEPROM is just a prototyping method which I am using. I'm using an Atmel I2C EEPROM. So we'll see that in the demo. So Microelectronica is not releasing the EEPROM boards now, but they are working on a better standard. So there are some disadvantages of keeping a plain I2C EEPROM as an identifier mechanism. So we can see the Microbus driver as the driver that takes in the add-on board specific information from the identifier stored on the non-volatile storage on board the add-on board, and takes the port specific information, and it combines and translates to code the data to the device driver probe. The add-on board identifier format that now we use is a extension to the Graybus manifest. The Graybus manifest is a data structure which contains the manifest header along with a set of descriptors. It was used within Graybus to describe the capabilities of a module. The manifest source is very similar to INA style configuration files. The current Graybus descriptors cannot accurately describe a device with enough information to provide the device driver probe. The majority of the add-on boards require interrupt information for the successful device driver probe. Few require additional name properties, few require named GPUs. So we are adding some new descriptors, namely the Microbus descriptor, device descriptor, and the property descriptor to allow us to describe an add-on board with enough information for the device driver probe to happen successfully. Chris, I think I have lost the control to switch the slides. Okay, thank you. So this is a first descriptor we are using to describe. It's a Microbus descriptor. So the Microbus descriptor tries to describe the prior states of the Microbus that should be set up for the add-on board to work correctly. So take an example for an add-on board with a active low reset on the reset pin on the Microbus board. So we need to pull the pin high so as to prevent reset during the runtime. So for a device having an interrupt, then we need to configure the pin as an interrupt GPIO input. Then some deviations from the Microbus standards allow all of the pins on the Microbus port to develop as GPIO. So the I2C pins, the SCL, SDA pins can be in their default states or in the GPIO state. So the Microbus descriptor tries to describe the pinmux states and the GPIO states that should be set up prior to the device driver probe so as for the add-on board to work correctly. So next is the device descriptor. The device descriptor is used to describe a single device on an add-on board, and it actually contains in the information from structures SPI board info and I2C board info. But even though those structures are used, but it can actually fairly describe other devices relevant to the Microbus. So the other SerDev and platform devices. So the device descriptor is a sorry, I forgot to mention that the Microbus descriptor is also a fixed length descriptor, and we will have only one occurrence of the Microbus descriptor within an add-on board manifest. The device descriptor is a fixed length descriptor, but there can be multiple instances of device descriptor on a single add-on board manifest. Multiple instances come up when there are more than one device on an add-on board, which we'll see in some of the examples. So the device descriptor, the main entry is the driver string ID, which corresponds to a string descriptor, which is the device ID for the add-on board device. Then it's the protocol which the device speaks. So hex B is the corresponding Graybus protocol for SPI, and this is the mode SPI mode, and the rect value for an SPI click will be the chip select that the device uses. So the rect values for an SPI add-on device can be 0 or 1. This is used to consider the deviation from the Microbus standards, that the reset pin on the Microbus port can develop as a SPI chip select for the device. So for some add-on boards with 2 SPI devices on board, say one chip select will be on the actual Microbus port pin chip select, and the other will be on the reset pin. So rect 0 corresponds to the device having chip select on the CS pin, and rect is equal to 1 for the chip select on the reset pin. Then IRQ1 is the, so we have a mapping for the Microbus pins. So the 0 will be mapped to the PWM pin. So we will describe about this in a later session where we write a few add-on board manifests. So now we can see the IRQ1 maps to the interrupt GPIO, interrupt pin on the Microbus port. So this information is encoded as a relative position within the device descriptor, but this will be translated to the actual GPIO within the Microbus driver by combining the data from the device driver. So the IRQ type is the type of the IRQ defined under Linux interrupt notice. So here the device is an Ethernet controller which needs an interrupt to be serviced on the following edge. The last descriptor we are using implemented within the Graybus manifest is the property descriptor. The property descriptor is used to pass additional named properties or GPIOs to device drivers. In case the properties are passed to the device drivers using the Unified Device Properties API defined under Linux property.h. And this property descriptor will be mapped to a corresponding structure property entry. So we have all the information to map the property descriptor to a property entry. We have the type, then we have the name of the property, and then we have the value. This value can be a single value or an array, and it can fairly describe all the types of properties that can come under the property entry structure. So in case of named GPIOs also, we will be passing it to the Microbus driver in the same manner. But for the GPU's case, the Microbus driver will actually translate the relative position passed within this descriptor to the actual GPIO by combining the data from the device tree overlay. We'll see this in an example. So I would also like to add a proposal to add the Microbus as a bundle class within the Graybus. So adding Microbus ports over the Graybus has an advantage of using different transports. So a transport can be simply a UART or a wireless channel. So I think in Chris Fred's presentation, he will describe more about the Graybus transports. So I'm proposing to add a new bundle class for the Microbus port. So under this bundle class, there will be C port protocols corresponding to each of the buses and other peripherals, PWM and GPUs on the Microbus socket. So I have recorded a few demos with some of the supported add-on boards and the board.org boards. I'm sharing the video here.
This is a functional demonstration for the Microbus driver. The hardware we are using is a BeagleBoard.org Pocket Beagle with the header soldered on its Microbus ports, another Pocket Beagle attached to a TechLab cape, and a BeagleBoard Black Wireless with the Microbus cape and a set of Microbus add-on clip ports from Microelectronica. Let's see the first demo with a few add-on clip ports on the Pocket Beagle Microbus ports. This is the kernel version we are using. We can see that the Microbus driver has registered itself as a new bus type, but there are no Microbus ports registered under the driver. For registering Microbus ports, we need to provide a suitable device tree overlay which contains the information about the Microbus port. Now we are enabling the device tree overlays corresponding to the Microbus port 0 and 1 on the Pocket Beagle. After a reboot, we can see that the Microbus driver has been loaded with the two Microbus ports, port 0 and 1 registered on the Pocket Beagle, and the default pin control pinmux settings are selected. You can see that as there are no add-on clipboards loaded, the default EEPROM probing fails. Once the Microbus driver is loaded and the ports are attached, we can see the corresponding Zephyr entries. So the new device entry helps us to write a new manifest binary blob to the file so as to load a new add-on board. The delete device allows us to remove an added clipboard, and the rescan interface will trigger a rescan on the onboard EEPROM. Let's look at the manifester tool used to generate the manifest binary from a manifest configuration file. The usage of the manifester tool is as follows. Now we have loaded the Pocket Beagle Microbus ports with two clipboards. The Pocket Beagle Microbus port 0 has a geomagnetic click, and the Pocket Beagle Microbus port 1 has an MPU IMU click. So now we are trying to write the manifest binaries to the EPROMs on the clipboards. So we are probing the Atmel EPROM driver, and then we are writing the EPROM binary manifest binary contents to the EPROM. We are probing the EPROM on the Microbus port 1 and then writing the manifest binary contents corresponding to the MPU IMU clip to the EPROM. After a reboot, we can see that on the Microbus driver probe, the EPROM will be scanned for the manifest, and then the corresponding device drivers will be loaded. So we can see that the Microbus port 1 has the MPU IMU click registered, and the Microbus port 0 has the geomagnetic click registered. We can also see these devices under the IIO bus. Now let us remove these devices on the Microbus ports and try adding new devices using the rescan interface on the Microbus driver. So the rescan interface resistance entry helps us to trigger a rescan of the EEPROM on board the Microbus port, which helps us to load a new add-on clipboard without probing the Microbus driver again. So now we have replaced the clicks with the new clicks. We have the Ethernet click on the Microbus port 0 and the microSD click on Microbus port 1. Now we are triggering the rescan of the EEPROM contents to load nucleus. So now we can see that the Ethernet driver has been loaded and the Pocket Beagle has connected to the local network. You can see the MMC SPI driver loaded and the SD card has been recognized correctly. Microbus port 1. Now let us see an example where the onboard click port does not have an EEPROM. So now we can write the manifest block, binary block directly to the new device interface on the Microbus port, and we can see that the driver probe happens successfully and the device is registered. So we have the example of the RTC6 click on the Microbus port 0 and it has registered itself as an RTC.
Okay, that was a great demo, Vaishnav. Do you want to do some question and answers for a little bit?
Yes, Chris. So Maximia has asked that some of the items in the device tree fragments for the Microbus port are mostly platform specific. So in the current state, some of the pinbox settings are actually platform specific, and that those needs resolution. And we have not yet tested on different platforms other than the BeagleBot or targets. And it will be fairly easy to reproduce the work on other targets like the Microbus Cape with on the Raspberry Pi and other devices. So, as Robert asked, the INA style format is used by Graybus to describe the manifest source. So, we are actually trying to keep the same kind of source here as well. So that's the main point of choosing the INA style format. So, like we described earlier, and then the proposal also aimed to add Microbus ports over Graybus, so we can keep the same tool to generate the identifier manifest binary, and then the manifest source and the binary data structure formats will be same. So we can I have one more recorded session for the how we can write add-on board manifests. I have recorded this session since it's switching on data schematics or the presentation
write
will
the
be
manifest source for a custom
efficient.
Microbus add-on board. Hi everyone. Let us look at how we can write the manifest source for a custom Microbus add-on board. The first example we are planning to see is the Ethernet click add-on board, which has the ENC28J60 device on the SPI bus on the Microbus port. The device has an active low reset and generates interrupts that needs to be serviced at the falling edge. Let us look at the manifest source for the Ethernet click. We follow a standard to include the kconfig entry for the device driver in the manifest source comments. Lines starting with semicolon are considered as comments in the manifest source. And then we have the manifest header where we specify the manifest version. And then the interface descriptor where we specify the vendor and product string IDs. These are mapped to a corresponding string descriptors within the manifest. So we have the vendor ID as microelectronica and the product ID string as the Ethernet ETH-click. Then we have the Microbus descriptor where we describe the pin states on the Microbus ports which needs to be set up for the add-on board to work correctly. So we have an entry for each pin on the Microbus port, and then each pin can be set to a default state or one of the GPIO states. So a PWM pin can take its PWM state or one of the GPIO states. So in this case, we are setting the interrupt pin as a GPIO input, the SPI pins as a standard SPI mode, and then the reset pin as a GPIO output high, since the device has an active low reset and we need to prevent a reset happening. Then we have the bundle and seaport descriptors. These descriptors are not currently used within the Microbus driver, but they describe the Graybus resources that the device uses. So we have a bundle of the class GP5, and then we have 3 seaports which corresponds to the device's resources used. So we have 2 GPIO seaports on seaport 1 and 2, and then we have a seaport with the protocol hex B, which maps to the SPI protocol, Graybus protocol. Then we have the device descriptor, which describes the device properties. We have the device driver string ID, which maps to string descriptor for the driver. And we have the protocol hex B maps to the SPI protocol. Then we have the mode, which maps to the SPI mode of operation. And then we have the rec value. The rec for SPI devices will be the chip select relative to the Microbus port. 0 will correspond to the devices that use the chip select default chip select pin on the Microbus port, and 1 will be for the some devices that use as the reset pin on the Microbus port as a chip select. Then the max speed is the max speed for the on the SPI bus the device can operate. And then we have the IRQ. The IRQ value for this device is set as 1, which is mapped to the Microbus pin in interrupt pin on the Microbus port. Even though the IRQ value is a relative value in the manifest, this will be translated to the corresponding GPIO IRQ for corresponding to the interrupt GPIO pin on the Microbus port to which the add-on board is attached. The IRQ type can take any value which is defined in the Linux interrupt.h. Now let us look at a different
sorry, Arvind, due to the shortage of the time, I have to stop the other video sharing also. If you are interested, you can take a look at the video on YouTube. So I'd like to mention some of the open problems or challenges we are facing. So the device drivers not using the unified device properties API to fetch the properties will not work with the mechanism of sending the named properties using the unified device properties API. So the drivers which use device property read calls will work, but OF property read calls will not work. And similarly, the drivers using the devam GPID get calls to get the named GPIOs will work, but the calls to OF get named GPIO will not work. And then we are not also able to describe devices which has child nodes in the device tree fairly so that for a successful probe. And then we have an open problem which Chris Fried has also mentioned in the chat, the PMX handling when adding Microbus ports through Graybus. So this is the plan for the Microbus driver to add the several device supports. There are a few GNS GPS add-on boards to be supported. Then the microelectronica is working on a new Microbus v3 standard, in which there will be an onboard identifier mechanism. It won't be an H2C EEPROM, which we are using now. And then the focus will be on adding Microbus ports over Graybus and provide proper documentation. Thank you.
Hey, Vaishnav, great presentation. Really, definitely looking forward to playing around with a few Microbus clicks myself. I've got an OLED display, which is kind of interesting, and an accelerometer. I think the SPI, one of the OLED is SPI, and then the accelerometer is I2C. Do any of our attendees have any questions?
So it's not clear to me why you're using Graybus at all here. It looks like you're adding generic properties to the Graybus, which we already have to describe the hardware, and we already have two ways to describe hardware, ACPI and DT. My other comment is the original intent in Graybus was we were going to do DT overlays to describe the downstream hardware, but never got to that point with the project.
Yes, so that was what we were also facing when trying to add devices. So I think Graybus was none of the Graybus devices actually use a Linux kernel driver within the kernel. And also, like in the current state, it might not be very clear that why we use the Graybus. We include the Graybus in the scope of the Microbus. So we are actually working on adding the Microbus port as a bundle class in Graybus, and so that we can transport a Microbus port on some other target. So, for example, a microcontroller target, and the corresponding device driver can run on the Linux host, for example, a Pocket Beagle.
Well, you mentioned that the device property APIs are not used for a lot of drivers, but that probably means that the DT APIs are used already. So you're creating a bunch of work to go convert all that and also define the same thing in the Graybus manifest.
Yeah, I guess the question is, so why are we putting Microbus over Graybus, right? And I guess it's just because there are some very Microbus specific nuances that we need to handle, or I guess Vaishnav needs to handle, and beagleboard.org needs to handle, that probably were not covered 100% with the vanilla Graybus spec. But I totally agree with you. And actually, it's funny that you mentioned device tree because I'll be talking about that later. So that's just my 2 cents.
I mean, I think another motivation was that we have no mechanism for device tree overlays at runtime, which some users on the BeagleBone boards get annoyed by because they don't like that they have to reboot every time they would like plug in a new click module. So this was seen as some way to have like hot pluggability since we're unlikely to get device tree overlays. Yeah, runtime.
Is hot plugging really safe to do?
I mean, I think so. There's also no like runtime pinmuxing mechanism. So like people were getting annoyed that just to do simple changes, they would have to reboot. So that was one of the motivations for looking at Graybus, because, you know, it has the ability to describe things during runtime, you know, because the Cape manager is a thing of the past now.
I think the big missing piece here is the kind of connector binding and how we define that. And there's been some work on it. And Like K-map GPIOs is something that's been done, but how to handle SPI and I2C and other things is not.
You mean like the deep device tree connector thing? Like I remember that from a few years ago, but I hadn't
Yeah,
seen.
there's been a few attempts, and it's just never made enough progress.
Yeah, because then that would also, I think, handle these use cases as well. But I think we kind of looked into this because there wasn't really any, didn't seem like there was any active alternative.
Hey everyone, sorry, we gotta try and stick to the schedule. I think that's a really good point though, Rob. And I'd be happy to open up a hack room if we want to chat a bit more. But I just want to say thanks, Vaishnav. That was a great presentation. You did a great job. And thanks for all your contributions to, everything. Microbus, Linux kernel. Rob, did you have any other comments that you wanted to quickly make, or?
No, not right. We can take it to a hacking room.
You might have some questions for me later too, because I think that you touched upon some of the things that I was addressing. So hopefully we can pin some things down later on.
Sure.
Thanks.
Thank you, Rin.
Okay, so I am just about to hand it over to a former colleague of mine, Michael Magyar. He's a whiz kid. That guy's amazing. And he will be presenting on OpenThread implementation in an embedded Linux device, I believe for a border router, but please correct me if I'm wrong. In any case, let's find Michael in the list. Let's see, Michael. Here we go. There we go. Okay. And trying to make him presenter at the moment. Oh, here we go. There we go. All right. All right, Michael.
Do you want to load the slides for us for him?
Yes. Thanks for that. And we'll set the current one to using the thread networking protocol. All right, Michael, this is you. Are you good to go?
I think so. Thank you for the kind introduction. The premise of the talk did shift a little bit. My focus has been more on border routers in the past little while, but the slide content is more of a generic thread overview. It's kind of how things fell out, and a bit of a pitch as to why thread might be a compelling technology to use for the IoT and some of the applications and problems that it already starts to solve compared to other technologies. So a bit of an agenda. So we're going to do a quick introduction about MMB networks and myself. As Chris mentioned, we used to work together at MMB Networks, and before that, when I was interning at Flextronics. The other bit of fun trivia, the BeagleBone White, excuse me, was actually my first introduction to embedded Linux back when I was an intern. So just fun trivia there. Moving on the agenda, we're going to take a quick look at IoT landscape, a quick comparison of some IoT technologies, similarly an introduction to Thread and some thoughts about why one would use Thread over other technologies. Then one piece that is, I think, somewhat unique for Thread is the existence of OpenThread, an open source implementation of the Thread protocol that anyone can try out and hack on and do some interesting things with. Next up is talking a little bit about a border router. Why do we want it? And then getting one running on a build root-based system. and then a quick video demonstration of forming a thread network, joining a device, and having that device be able to ping my off-mesh IPv6 accessible laptop and an IPv4 accessible cloud resource. So quick introduction. So MMB Networks, we're a technology company in Toronto working to bridge some of the gaps from the technology and the application layer and letting some of the biggest brands and some smaller brands and companies as well connect their wireless devices and bring them to market. So anything from smart meters and utility, smart thermostats, locks, lighting solutions, all sorts of different IoT where you need that plumbing to get the data from sensor to edge node to cloud, and even doing some processing on it in between. Quickly about myself, I started as a firmware developer in 2014. I've now since grown and taken over maintenance of MMB's Rapid Connect Linux gateway, and find my day-to-day work is focused around that embedded Linux product and our projects that touch on Bluetooth, Wi-Fi, or Thread. So, a quick little IoT landscape overview. I wanted to sort of split up and call out some common home and commercial IoT technologies and divvy them up by ones that define everything up to the application layer, and then those that only define up to transport layer. So the one that I am most familiar with is Zigbee, where all of the thing behaviors and messages are defined by the Zigbee cluster library. So Zigbee controls that stack from top to bottom and defines every piece of its interaction. It is it's not IP based. It is custom to itself. Similarly, Bluetooth Low Energy. All Bluetooth devices are, or I shouldn't say all, but generally they're going to be using some form of GAT characteristic to define the thing. Bluetooth Low Energy is very ubiquitous in smartphones, laptops, and some IoT devices, door locks, lights, and again has a somewhat rigid structure and rigid requirements, being GAT-based. The new Bluetooth on the scene, Bluetooth Mesh, starts to address some of Bluetooth's one-to-few or one-to-one relationships and allows for a many-to-many relationship through the concept, by adjusting Bluetooth's beaconing and attaching the mesh payloads within a beacon. So this still very much defines how you're going to get a message across, what that message payload is going to be, and how you're going to interpret it. Similarly, Z-Wave has its own implementation from all the way up the stack to its own application layer and on its own sub-gigahertz modulation. A common factor with all of these application layer technologies is to have them interact with other devices or cloud resources usually require some form of application gateway in the chain to translate messages to or from one technology format to the other. So in the case of Zigbee, you'll see Zigbee gateways. An example that many might be familiar with is the SmartThings Hub or a Philips Hue Hub. Both of those offer Zigbee low power communication to the end devices, and then some sort of IP-based communication to the gateway or hub itself. To contrast that a little bit, I want to look at Wi-Fi 6 low pan, and Thread. Wi-Fi being...
Michael?
Yes.
Just a quick question. So Bluetooth mesh with the IP protocol, that would use 6LoWPAN as well, right?
Yes.
Okay.
I believe
So
it's...
there's no gateway or translation needed at that point.
Right. When you're carrying 6LoWPAN over BLE, that's true. You'll still need a Bluetooth device there, but at the same point, if you have a 6LoWPAN 802.15.4, you're going to have some device doing translation there as well.
Okay.
No, that's a good point. I kind of glossed over that a little bit to try to push towards Thread. My apologies, and thank you for bringing that up. So Wi-Fi is ubiquitous, it's IP-based. It doesn't care what the application is that it's transporting. Similarly, 6LoWPAN is also IP-based with a compressed IPv6 packet. Specifically, what I'm somewhat familiar with is over 802.15.4 in the 2.4 gigahertz band. So where someone would use it for a smart home setting or a commercial installation. The new kid on the block is Thread, builds on top of 6LoWPAN, adds routing, security, commissioning, and a certification program through the Thread group, starting to guarantee interoperability and compatibility between devices. One of the major points that I've seen working on application gateways, specifically Zigbee ones, and one of the benefits that would come from using an IP-based technology would allowing for multiple applications to interrupt and coexist on the same network. Right now, if you have a Z-Wave, bad example, Mike, but if you don't have that sort of easy interop with those other technologies, barring the exception of if someone's doing a 6LoWPAN over Bluetooth. So some of the sample application layers that I've had the opportunity to touch, so obviously Zigbee, OCF, KNX seem to be big players in buildings, building and lighting, good old CoAP, and then the other new kid on the block is Project Chip, which is a project by the Zigbee Alliance and some of the biggest names in technology. So just to address some of the questions coming up in the chat, yes, I believe MLE messaging or thread management framework messaging would be required. But there might be ways around that because the commissioning just ultimately just requires that DTLS handshake between the commissioner device and the joiner. So quick introduction to Thread. So why Thread instead of other IoT technologies? So Thread offers relatively simple network installation, startup, and operation for the user, not necessarily for the developer right now, but the end goal is for the user experience. It should be as simple for the end user as possible. Out of the box, provides secure joining and encrypted and secure communications with the Thread network key. It will provide good range. Mesh networking would provide sufficient range to cover an entire installation. There's no single point of failure and self-healing. Unlike a Zigbee network, where the coordinator is the root of that network and plays an important role in the network's operation, the Thread leader can be any router or router eligible device. So if you have nodes dropping off on a Thread network, the network will just adjust promote router eligible devices to routers as needed, or demote them again as needed. Thread is low power, being based over IEEE 802.15.4, and it is built on existing standards in silicon. So if you have a radio capable of doing 802.15.4 communication, then more than likely you will be able to run Thread on that radio, either from a vendor-provided stack or more likely a platform layer in OpenThread. Sorry, am I going too quickly? Or
No, not at all. I just wanted to, this might ring a bell. I don't know if you recognize, I'll turn my camera on. I don't know if you recognize this little guy. Oh, there it is. Stefan Schmidt probably recognizes it. Anyways, I remember when we assembled these in the bottom of MMB Networks lab.
yeah,
AT-USB.
I actually have a couple of them not on my desk here, but in the drawer beside me.
It's great to see them with a red PCB. I only have them with green.
Oh, mine are purple from Osh Park.
Ah, okay, I see. All the new batches are getting hand flashed by me nowadays. So every now and then, if there's a stock gets low, I get a batch of like 100 of them, and then I'm flashing them by hand.
Oh no! Well, I've got I think 2 or 3 of them, and I still poke around with it every once in a while, but not that often anymore, unfortunately. Sorry, I diverge. So the one thing to note with Thread is that there is a Thread group that for access to the standards and the IP protection, Thread group membership is required. I don't remember it being overly expensive, but there's quite a bit of benefits to joining the Thread group. In addition to full access to the specs and documentation, there's access to the test harnesses, the technical committees, additional white papers and resources, but that is pretty much up to you, like where you're taking it with your product, and whether you're going for Thread certification or if you're just hacking on something at home.
Okay, just a quick question on that, because I remember when I started looking at Thread, that was way before OpenThread was announced, and that was really in the initial phase when they had the spec just behind closed doors. I know they opened it up at some point. Is it back behind membership rules now, or is membership only for things like certification, test harness, and IP related stuff?
IP protection. Yes, that's my understanding, that you'd be able to download, there's like a request form to get the Thread 1.1 specification. The 1.2, I believe you would have to be a member to access still, and then any of the future work would still require membership.
Okay, so the model would be for just a hobbyist developer or something, you get the released version, it's no problem, but if you want to do products, you want to be a member, or if you want to influence the working groups and something like that, then you want to be a member.
That's correct. Yep.
Okay, thanks.
No problem. Just to qualify, I'm not a Thread group representative. I would suggest to go online and check their listing of benefits and requirements. I'm not an expert on that. MMB is a Thread group member, which gives me access to all the resources, and I can speak to them, but I can't speak to what your requirements would be and how you would want to approach that.
Yeah, I didn't ask for legal advice or something. I just wanted to understand it a bit better, because I know that they've been swapping back and forth, so I wasn't sure how that is right now. So I understand it. If you really want to do a product with that, then you want to be a member, basically.
Yes. I'm just clarifying so that nobody later on in the video misconstrues what Mike is saying and thinks that, oh, it's a free-for-all, there's no requirements. Okay, so we're going to move on to talking a little bit more deeply about Thread. So Thread defines different device types and roles. Those are full thread devices and minimal thread devices. A full thread device would be something like your border router, your router eligible end device, and your full end device. So the main key difference between a full thread device and a minimal thread device, if memory serves, is that a full thread device will maintain a routing table, whereas a minimal thread device will not. They will only speak to their parent device, who will be responsible for routing any messages to and from that minimal thread device. Device roles are determined by the stack using meshlink establishment messages, with the network adjusting and promoting router eligible end devices to routers as needed, and demoting again as the network requires. All nodes will have a link local and a mesh local IPv6 address. And if a border router device is present, a global address may be configured through that border router, either using Slack or DHCP v6. As you might imagine, a lot of the interesting applications with Thread happen when a border router is in play. So a local link address will be an address just on a one-hop radius. So a node that can hear another node, whereas a mesh local will be everyone on this mesh network. Everyone effectively within the PAN. All right, so thread commissioning. This is a bit of a complicated topic, but is one of the pieces that I think from consumer perspective will make it very attractive. And that's specifically the concept of the external commissioner, which in many cases would be a mobile phone. So joiner devices must securely communicate with a commissioner and establish a DTLS handshake. So this process, sorry, perhaps I'm jumping ahead there. So a commissioner is required for a joiner device to join a thread network. And usually that requires some sort of human intervention. For the home use case, although Thread 1.2 and future work is talking about how to do this at scale and more commercial settings, there's a human interaction to enter the joining passphrase of a joiner device into a commissioner, whether that be a native commissioner on an on-mesh device, or an external commissioner, an off-mesh device. The process is roughly that a joiner device will seek out a joiner router and announce that it is attempting to join. If the thread network information is aware of a commissioner, that is to say, a commissioner has established a secure connection with the thread network, that handshake will be relayed from the joiner through the joiner router and any other routers in between until it reaches the commissioner. In this diagram, I've drawn the external commissioner connected to a border router, as I think that will be the most common consumer use case. So generally this would be done over Wi-Fi to a mobile device and is handled by functionality called the border agent, which can be on a border router, but they are not a border agent does not need to provide border routing functionality. It can be just an agent that relays commissioning messages. Any questions on that one? Because it's a very high level view of the commissioning process. There's entire white papers on how this process is done in Thread.
I probably should have read up on this a little bit ahead of time because I'm asking a question that's somewhat naive, but I haven't really investigated the Thread specification in that much detail. But I'm just wondering what kind of sort of security mechanism it is for authentication. Like, what kind of authentication mechanisms are they using underneath the hood? Is it like sort of a public key-based sort of mechanism?
So it's using, I'm just looking it up because I don't remember this off the top of my head, a password authenticated key exchange JPAC on a NIST P256 elliptic curve. So it is a public key exchange.
Okay, very cool.
So the way that I've done this in practice, and we'll see it in the video, is there's two exchanges that occur. The first exchange is for the external commissioning device to authenticate with the Thread network using the commissioner PSK. So on forming of the Thread network, either auto-assigned or user-assigned, and then that commissioner PSK will need to be entered into the external commissioner for it to do its handshake with the leader on the Thread network. Then there's a separate handshake, the joiner using the joiner PSK for a joiner device to establish a secure connection with the commissioner. Okay, so I think that gives a bit of the overview on Thread. There's a good chunk more, but a lot of the routing functionality has already been addressed. It's really that the node types and the commissioning that I've seen people have questions on. So I want to move on to talking a little bit about OpenThread. I'm going to call it standing on the shoulder of giants. What's a little bit unique about the Thread world compared to Zigbee or Z-Wave is that there is an open source BSD licensed Thread implementation as OpenThread available for people to hack on. It's relatively easy to get going, supports all the features in the Thread 1.1.1 specification, and is itself a Thread certified component. The implication of that is that if you're taking a product to market, excuse me, you can certify by similarity. So there's a process that would decrease the amount of effort that you have to go through to certify your product when you are using a Thread certified component. OpenThread also supports border routers through the OTBR POSIX project, and they support multiple different designs from fully integrated system on chip to network coprocessor and radio coprocessor designs. And they're supported right now by a wide range of vendors and stocks. The multi-platform support is handled by a very nice separation between the thread libraries and the platform-specific implementations, allowing the same thread core to run on a Nordic sock, an XP sock, Scilab sock, with just the Flash timer radio APIs being platform-specific underneath. Out of the box, CLI and NCP sample applications are provided, and we'll see the CLI running in a little bit on a couple of my devices. So I just want to throw in the disclaimer, we're not affiliated. I am not affiliated with Google Nest or OpenThread. We're just very happy users and hopefully happy contributors with some of the work that we've done on top of OpenThread for our customers. So I wanted to call out the radio coprocessor design specifically because I found some of my colleagues had difficulty with this because it's a little bit different than most NCP models, especially in the Zigbee world. Specifically, the difference being that in Zigbee world, the Zigbee stack tends to live on the 802.15.4 sock, and the vendor will just give you some hooks for your host processor to interact with it. The OpenThread radio coprocessor design moves the entire OpenThread core and APIs onto the host, so letting you take advantage of all the resources available to you on your Linux device, or if you're doing a situation where you have one high-powered MCU and one lower power MCU, and you can take advantage of that. So this allows for the use of some lower cost and lower performance 802.15.4 socks, things with perhaps less RAM, less flash, because it is a very minimal image. The communication between the host processor running the OpenThread stack and the 802.15.4 sock is done using the Spinal protocol, a general management protocol developed and released by Nest with an IAT draft document to go into the specifics. The Spinal protocol can either go over UART or SPI transports. Specifically, I've been using UART for my implementations. So now we're going to talk a little bit about border routers. I think I danced around it earlier on. But while the border router is listed as an optional device in a thread network, it's really the piece that gives it the most power, in my opinion, with its role of relaying data between the thread and IP-based networks, either connecting via Ethernet or Wi-Fi or up to cloud resources, its use in commissioning. It's really an integral piece of a thread network and a thread system. And the most key thing is at network layer and at transport layer, so it's just IP packets that it's going to forward from the internal thread interface to the external, and vice versa. Going to handle packet filtering, address translation, any sort of firewall or infrastructure settings that you need to take advantage of, VPN tunneling, and have the border router take part in the external network environment. Oh, okay, I gotta pick up the pace. With the biggest value add being the transparent end-to-end IP communication. I'm gonna jump ahead. I found with a lot of people who are more familiar with the Zigbee world and have difficulty conceptualizing the border router, I like to say that the border router is a piece of infrastructure. Just the same sort of way that Wi-Fi routers and Wi-Fi access points specifically brought together mobile phones and laptops and computers and the ubiquity of those devices that we enjoy today. thread border routers, in my opinion, will bring the things and the Internet of Things to a standard IP-based world, and will give it that same sort of ubiquity. So building a border router, so the OpenThread border router OTBR POSIX project out of the box runs on a BeagleBone Black and a Raspberry Pi. It is also completely possible to package it on Buildroot, which is what we're doing for the Rapid Connect gateway. So it took a bit of effort, but it's completely possible to package that. When running OTBR POSIX, it will create a ton device, WPAN0, which you can now start applying standard Linux networking tools and techniques against it. So just enabling IPv6 forwarding, IPv4 forwarding, bringing up a Tega instance for NAT64 using the well-known prefix, or in a more custom solution, a site-administered prefix allowing for NAT64 communication on your local network, configuring by 9 for specific DNS zones. Okay. And on the node side, MMP's implemented commands for find DNS Slack for locating border routers hosting DNS servers, allowing you to do a DNS resolve, your custom service, and be returned back that appropriate address on your local network. Out of the box, OpenThread tends to hit Google DNS64 servers in the cloud. And we found that a lot of our customers don't want to interact with the cloud. They want to interact more with local devices. All right, demo video. Okay, let me see how to pull up my YouTube video. Okay, let's try. Sorry for the delay.
Hey, Michael, you should be able to upload. So if you click on the plus button, you can select upload a presentation, I believe, and then you would just add a link instead of the
Yep,
PDF.
there we go.
Or you got it? Okay.
There we go. Add video URL. So this is just me finding my border router on my home network using the OpenThread web interface. The thing to admit is that the integration with the Rapid Connect web interface is not quite there yet, so I have to leverage the OpenThread one for this. So this just creates our thread network. Oh, okay. I'm not sure if the video is still playing for you guys, but it dropped off for me.
Sorry,
so,
I thought that was my fault. Let me. I was trying to upload a slide. Go ahead. Sorry. Go ahead.
no problem.
I don't know if you can continue where you left off.
I'll just track ahead, and please cut me off as soon as I go over time. I don't want to cut into anybody else's time. So at this point, we log into our border router, use OpenThread control commands, and see that our state is leader. The next step will be to begin on mesh, begin the on mesh commissioner with a joiner PSK. There we go. So our joiner PSK is the join me at the end of that string. So we are telling the commissioner that we are going to add a joiner with an infinite timeout with that joiner PSK. On my top right terminal, I am serially connected to another thread device. I bring its network up and I just tell joiner start with the joiner PSK. Now we'll confirm by looking at the router table between both devices that we are in fact on the same network. We have the same RLOC address, or we can see the same RLOC address on both devices. Taking advantage of some RADVD and some scripting to set up our off-mesh route and assigning setting up advertisements for Slack assigned addressing on my home Wi-Fi. And then just to help me out, grabbing from the configuration what that pseudo-random generation was. And then it is just a straight ping from my thread USB dongle through the border router, through my home Wi-Fi, onto my IPv6 connected laptop. The last one will be a ping using the NAT64 well-known prefix to amazon.ca. And again, it works completely seamlessly. Okay, and now. No, that's the end. So.
Okay, great. I was just going to say, does anyone have questions that we could pose to Michael really quickly? Because we're just a few minutes over. Okay, Stefan Schmidt has a question.
I would jump ahead here. I mean, that's something we can also take offline or somewhere in a hacker room or something, so I don't want to cut too much time. So, as you might know, I'm the maintainer of the 15.4 stack in the Linux kernel, so definitely I have a view on that. And when I looked at OpenThread, that might be actually a few years ago, but I think Spindle is still in the same situation. So you would put everything inside the firmware, even in the radio co-op thing they have. So that means everything like 15.4 control and 6 low-pan control, especially like compressions and so on, that would all sit in the firmware of the microcontroller, right? There's no control for that on the Linux side. Is that correct, or?
Not in the RCP implementation.
Okay.
In the RCP implementation, that logic moves from the MCU up to the host.
Even things like things like IP header compression and max header compression, all these kind of things.
I would have to check that, but my understanding is all of that is also moved over to the host processor in this configuration. Okay,
but it would reside in the OpenThread daemon running,
yes,
getting fed by Spindle and then creating the turn interface.
Yes.
And then you only have like the normal, I say, IP tools you could use on the Linux side. You have no integration with the network stack of the Linux kernel besides creating a network interface.
That's correct.
Okay.
Yeah. So this. Yeah, that's completely correct.
Okay, because
Sorry, I was just going to ask Michael, do you mind if I quickly take presenter and upload the next set of slides? You guys can definitely. We're actually technically on break right now, so if you want to just continue the conversation while I'm doing that, that's perfectly fine.
Okay, so because I remember that I talked to Jonathan and Martin from OpenThread before, as I said, that might be a few years ago, so I'm not sure how recent that all is. We have been thinking about how we could integrate OpenThread with the existing 15.4 stack in the kernel, but we never really found a good way for both sides here to work together there. I mean, I'm not saying one is the right approach and the other one is wrong. I'm not saying that.
Yeah.
It's just difficult to do that, because I was hoping that we could find a way to have like at least the all the file drivers and things like 6LoWPAN bits and pieces for compression and so on, sitting in the kernel stack, and then exposing a network interface from there and OpenThread sitting on top of that.
Yep.
But that would mean cutting out all the radio coprocessor design and spindle and so on. I think we tried that once. We had like an AF packet interface for data and like netlink for the configuration path, but it really never took off there on their side. So,
right.
Yeah.
So that's definitely an interesting idea, and Stefan, I must admit I'm a follower of your work on the mailing list. In previous life, Chris and I, with the AT Ben, spent a lot of time on 802.15.4 Mac layer primitives. So it's what you're suggesting is a very interesting idea. I honestly don't know what. I've not had a reason to look into how to go about that.
I mean, the thing is, if your focus is only thread, from a customer perspective, I completely buy that. It's a whole package. You get like, it's really appealing. I mean, you have like the whole thing, it's working. You have like the whole spec implemented in OpenThread. It's kind of certificated already. I fully grasp that. So I'm not arguing like our stack should be used as better or something. And we are really slow, and we are missing many pieces. I will come to that in my presentation. I'm just was hoping initially when Thread came out and then OpenThread came out, I instantly pinged Jonathan and tried to figure out if we can find a way to work together on that. And we tried to schedule up for a meeting, but then it never happened at some point. But that was, it's not like both projects don't like each other or something. It's more like we haven't found a way to make that work
together.
So that is why I was interested in seeing Spindle. That was actually the first time for me to see that they are proposing Spindle as an IETF draft. So that is actually interesting that they are doing that. Because kind of related, we are looking into something like WPAN USB, a generic host controller interface like Bluetooth has specified and 15.4 does not. So Spindle is not too far off, I guess, with some things, but I think it's really specific to some thread parts there. But yeah, I have to look into that, I have to say. Yeah, I just wanted to understand a little bit better where they are, at what stage are they now. So yeah, thanks for that.
My pleasure. So I must admit, for full disclosure, like I spend most of my time at a higher layer than that, like on the Linux environment, trying to make sure that I have support for my customers' applications on top of the border router. So I've not had a reason to dive into that layer, but it is definitely an interesting topic that might be worth a few hack days.
Yeah, I mean, as I said, if the decision is made that you're using Thread, then it's a really appealing package. I completely understand that. For me, it's more like it's still a hobbyist project, and I like to have the flexibility to run all kind of different things and maybe even try out different header compression techniques and stuff so on. So for me, it's more interesting to have like this kind of stuff sitting inside the normal Linux networking stack and integrating that. But I was always hoping to kind of find the right slicing point where I could fit OpenThread on top of that. But yeah, it's all a question of time and motivation and so on. Well, I will see.
Exactly.
Maybe in the future.
Yeah, and like I'm jumping into Thread because I want to rush forward to that endpoint and see the devices in use and the potential ecosystems and the innovation that could be drawn from it. That said, like the low-level hacking is always interesting. It's just a question of time, as you said.
Okay, yep. Thanks a lot for your presentation. It was really nice to hear that.
Thanks as well, Michael. I really enjoyed it, and I think I'm gonna check out those demos again because it's really nice to see kind of the finished product. And you guys have been around for quite a long time, so I mean MMB Networks has. So it'd be really interesting to check out that video again. So I just uploaded Michael Gilda's slides, and he's also got a small demo. But but we're on break right now, so we got about 4 minutes until the next presentation begins. And luckily, we can actually kind of sync up back to the schedule. So I'm just going to go on mute for a few minutes until we start up.
So one thing I would mention for anyone who wants to try this out, grab your favorite BeagleBone Black and a supported 802.15.4 sock, and it's really quite easy to get going on on those supported platforms. It's very easy to set it up at home and start toying around with it, and I hope that this encourages you to give that a try as well. We didn't go into a lot of the sort of headaches we had because our build route distribution for Rapid Connect Gateway has had a lot of customization for customer needs. And it's, for the first little while, there was a lot of head banging to get the border router to actually work on that and be integrated.
Yeah, it sounds very good. So we have a bunch of hack rooms as well. At any time, if anybody feels like they want to take the conversation offline, you'll actually get a video feed and everything. I think there are 5 hack rooms. So just grab whatever's available and feel free. Michael, thanks again. That was fantastic. Hi again. So we're going to be back from our break in just about a minute. And at that point, Michael Gilda of Ant Micro is going to talk to us about Renode.io, which is a technology that I'm very interested in. Michael, are you able to share your camera? Let me see if I can. I don't know if I need to give you any extra permissions at this. Oh, there he is.
On, and let me see the camera. Just so that the lighting isn't kind of completely in your face there. All right, I think that should work. Can you see me? Hi, everyone.
Yes. Yeah. How's it going?
Very good. Very good. Thanks for inviting me over.
Oh, yeah. It's my pleasure. Actually, Drew did most of the work, and I'm just so glad that he has your connection information. I mean, Renode.io is fantastic, but you're also part of the RISC-V board, I believe.
I'm not part of the board, but
Okay.
I am kind of chairing. I'm vice chairing I'm chairing content and vice chairing marketing for RISC-V.
Oh wow, yeah, it's a huge economy that's happening right now in that space.
Indeed, I have quite a bunch of stuff about RISC-V in this presentation. Wasn't sure which way to go, so a little bit of everything in a sense.
I might have to pick your brain at some point later because I'd like to do my own little RISC-V wireless micro at some point.
Oh yeah, that's kind of everyone's dream, I guess. Yeah, it's definitely a fascinating topic in itself. Like RISC-V, I could kind of give you a presentation on that on its own, but
for sure.
I'll try to.
Okay, well, without further ado, I'm gonna give the presenter over to you, and please go ahead.
Okay. Hey everyone, yeah, very nice to be here. It's my first time at Linux Plumbers, so sorry if I do something wrong or get out of the way people normally present stuff here, but I'll try to do my best. So as mentioned, I'll be talking about Renode, which is just an open source framework for simulating stuff. And of course, it can do a lot of things, and people have used it in many contexts. But for us, kind of one of the most important contexts there is continuous integration and testing. And I'm saying complex embedded systems here in this presentation because it can be any kind of like complex systems, and we really do kind of target that complexity. We really want to enable people to work with real stuff. Whereas, of course, it might be different things depending on who you are. And some people will be, of course, focusing on IoT, which is mostly the topic of today's track or microconference. But other people might understand complexity in a different way. And Renode's there to kind of handle all that, for better or worse, right? It does make it difficult to build this framework and support all these use cases. But at the same time, I think it makes it exciting too. And we can also see that handling this complexity gives us a very nice feedback loop for kind of thinking how to abstract out this complexity, how to make people think about systems in a more like systems-oriented way. Very often when people build embedded stuff, they're like, okay, I'm building my thing. I don't care about the rest of the world. We have to care about the rest of the world. We have to think about how these things are related, how they work together, because we need to map it to simulation. We have to build a simulator that actually caters for various things. So that gives us some kind of interesting results and ideas and concepts and features I'm going to talk about today. Okay. Yes, so just very briefly about us and where we're coming from. We're a service company that builds different kinds of embedded systems. We were founded 11 years ago now, and Renode was created almost immediately after we started because we saw that, okay, I mean, the way people build embedded systems is kind of weird. They don't use all the modern, kind of software techniques. They don't do much testing. How can that be? So we started a company. We just didn't know how you should do things, and we thought you should do them differently, and we created our own tools to enable that. And I guess that's a theme for us. We kind of work with open source to build new methodologies that kind of turn some things upside down and help you do things more effectively. And as Chris has already mentioned, we joined quite a bunch of organizations that are also concerned with kind of uprooting the existing status quo. RISC-V being, of course, the most prominent one, but also CHIPS Alliance, which is a great and fascinating. Oh, it's not listed. Sorry about that. CHIPS Alliance, which is a fascinating body that kind of wants to create open source FPGAs and ASICs and everything. Also, Open Power Foundation, which, of course, like you could say, it's a competitor to RISC-V, but we kind of, as all open source, we view it as a complementary thing. We're happy for both of those architectures to be gaining ground. The important connection point there, of course, is open source. Like open source is enabling us to do all the cool stuff that we're doing right now, and it enables us to think about it in very broad terms. Like, how can we improve the tools that we're building stuff with? But the constant stream of real customer use cases, like things that we build for our customers, gives us also some feedback needed to make those tools effective. And Renode is one of those. So yeah, we built it and we gave it its own brand. I'm even wearing a t-shirt. If you want one, just let me know. because we thought that it deserves like its own kind of identity. It's still a project that's kind of driven by our company, but it's become quite a bit more than that in the years. So yeah, if you're interested, just go to the website, and of course most of the stuff I'm talking about can be found in some form there. But I'm trying to kind of give you an overview of what's really interesting, and some stuff that you can't find on the website because we never have actually time to keep it up to date with all the great developments that are happening. So in short, why did we build it in the first place? It's a framework that kind of gives you a lot of capabilities to do various things. And continuous integration is one, but then there's also other things that people want to do with it. For example, many people use it for architecture exploration and research, especially RISC-V was mentioned. So in RISC-V, people build their own, SoCs, their own hardware. So Renode has turned out to be a pretty good tool to enable that. Also, some people have been prototyping things before silicon's available, and again, that's possible because we can simulate stuff we know how it works, but it's not yet there physically, and doing some kind of hardware software co-development. And it's funny because we always felt that this kind of complex IoT development is our most important use case. We still believe it's super important, but like over the years, we've learned not to kind of discriminate or like undervalue other use cases because people have been able to achieve quite awesome things with our framework. In brief, why we think it's cool. First up, it's very plug and play. It's built from building blocks, just like hardware consists of like processors and IOs, which are building blocks that silicon vendors kind of put together and then give you a kind of SoC that combines all these things. Similarly, Renode will kind of give you those blocks from which we can assemble platforms. Also, the kind of ability to simulate systems on different levels, like looking at both the SoC level, but also kind of full boards and entire complex systems of multiple nodes. That's kind of one thing that makes us stand apart a little bit. Also, it's a very kind of software agnostic framework. So we don't focus on say simulating Linux, right, or Zephyr or whatever. We kind of want to run whatever binaries and firmware you can run on any platform, meaning that we have to make sure that kind of all types of software work, which makes us pretty flexible. And it comes with batteries included. It kind of gives you a lot of demos up front. I mean, we try to make it simple to start, and you don't necessarily have to code a line of Renode, to actually do stuff with it. It's very driven by configuration files and all sorts of kind of neat little features that don't make you immediately go and have to read the code of Renode. You can kind of use it without getting your hands dirty, and then if you like it, you can of course get your hands dirty and improve it, but you don't really need to do that before then. So let me switch the slide. I was just focused in a different window. So as I mentioned, those kind of complex systems have many levels typically. If you look at it kind of layer by layer as an onion, this from you start with a CPU core in RISC-V, for example. You can have one core, but then you can perhaps get multiple cores in a heterogeneous system that kind of considers a CPU. Then you add peripherals, you have an SoC, perhaps you put it in a module, a SOM, then you take that module, you put it on the board, perhaps there's several modules on this board. Those kind of boards, multiple boards can constitute a device, and then you put together a bunch of devices and it's a system. So and companies or people and developers can focus on specific levels of this stack, and some people just don't care about the CPU and they kind of assume it's a given. Of course it's an ARM, and I don't care how it works. There's a compiler that takes care of that. I'm looking at the system aspect. Other people are completely opposite. They actually focus on developing the core, and they care about simulating on a more detailed level and so on. So we want to kind of take that complexity and solve it. So if you go to the first kind of context, you can use Renode in I think that's the most familiar level for most people, because if you've simulated anything with QEMU or something else, I mean, you'll probably see a lot of similarity in what Renode is to some other existing frameworks where There might be a CPU or a few CPUs, some peripherals, and you want to run some software on that and test whether it executes correctly. But then our focus goes beyond that. And if you look at a device, which has perhaps a screen or buttons or LEDs or a radio, we also want to simulate that. That's kind of a major difference, I guess. And if you kind of start looking at the entire board, you realize that's what actually people care for, right? That's what people work with day to day. So day to day, you don't really work with an SoC in its abstract form. You don't kind of grab a chip and put a program on it with a finger. You have a board, right? And like that board you typically interact with using some kind of an interface, and perhaps you press those buttons and you look at those LEDs, and Renode kind of allows you to do that only virtually. But then if you think about it, like if you put together a bunch of boards, it becomes even more cool, because you can start thinking, is my protocol right? Is my system behaving as it's supposed to be? Am I testing the right use cases? What will my users do with those wireless nodes that I'm trying to connect together? In fact, that kind of testing is the worst, the most difficult, and that's where we think most problems lie, and we can solve more problems than any other existing framework. And of course, in doing that, we can enable simpler use cases too. But especially when you get to this multi-node aspect, I don't think there's many viable alternatives, other than, of course, putting together physical setups, testing rigs. Some big companies do that, of course. They have 1,000 nodes somewhere in a server room. But like if you think about it, physical rigs are great. But what if you wanted to test what happens when you move the nodes around, or do some crazy stuff, or even press some buttons? We have like automated robots that press buttons. This starts getting very complicated very quickly. Whereas in simulation, I mean, you can do anything. The challenge is actually in figuring out what you want to do and why. It's the biggest challenge we struggle with, actually. We can implement all sorts of features that are oriented for building those complex systems. But then, I mean, what kind of features do you focus on, and what kind of scenarios do you enable? And that's driven by, what kind of customers come to us and ask for different things. So hopefully, like, you get some kind of a feeling what Renode is. And then we try to support different platforms and vendors. We don't care about the specific like architecture or vendor. We want to include everyone potentially. Here's some kind of a list. Of course, devil's in the details. Like there's some vendors for whom, like ST, right? We can support quite a large number of microcontrollers. Or there's Nordic, for whom we've just recently enabled the first platform. But I mean, ultimately, of course, we want to do them all. It's just a matter of bandwidth and demand and capability and similarity, right? I told you that Renode is based on those building block approach. And if you think about it, many of those chips are typically built with building blocks. So if the vendor is, smart, and their SoCs are kind of nicely structured and include specific blocks that you just kind of rearrange to get different chips, Renode has a very simple way of kind of making
Michael, I'm not sure. Oh, there he is. Sorry about that.
Was he back? I'm not seeing anything.
Yeah, we're able to hear. I think it must be Michael's side.
I think so, yeah. Worst comes to worst, we'll do we'll chat in the type window, and I'll announce everything that Michael's saying. No, I'm just kidding.
Hi guys, can you hear me?
Oh, you're back? Okay, good. Excellent.
I am back. Sorry about this. I just got kicked off the network, but it should be fine now. So I don't know where you lost me there, but what I mean is there are vendors for whom it gets very easy to support a lot of platforms like ST, because their chips are so similar to each other. And sometimes, of course, it's a bit different. It's all about the arrangement of the peripherals in an SoC and stuff like that. So, devil's in the details, but if you're not sure how hard it will be to enable platform XYZ, just kind of talk to us and we'll figure it out. Ultimately, what we base on is data sheets and public information. So it's not really that drastic. I think I need presenter rights again, because I think when I rejoined, I'm not. Okay, thank you. And you can see RISC-V and OpenPower here, of course, yay. And they are here on purpose. We're kind of super keen to enable open architectures, because like open architectures and an open source simulator and open source software play very well together. It's very easy to put together demos and kind of work with people and so on. Which is not to say that we kind of don't like proprietary architectures. Like ARM is really well supported, and especially Cortex-M, which is our major focus. So it's just that like RISC-V is kind of, or OpenPower, they're kind of cool in that you can do research on the architecture itself and talk to people building actual chips on a very detailed level, and you don't really get this problem of confidentiality and stuff like that. Yep, so someone, I think Drew linked to the list of boards already. This is just a selection. I mean, there's many more boards, but just to give you a feeling, it's stuff ranging from really tiny FPGA boards to like IoT nodes to gateway level devices based on RISC-V, for example. And I think one thing that needs mentioning, definitely why we can do these kind of things and why we support many platforms, is that we have a platform description format. Of course, the format itself is not that important. It's just a format that's kind of YAML-like. But that we have a format that is allows you to put together things in a simple way, where you just say how things are connected and what are the specific kind of, I don't know, IRQ connections, for example, or what kind of peripherals need to be initialized and at what places of memory. You can build a platform without actually writing code. All of this gets parsed automatically, your platform results, and then you can run software on that platform. So you don't have to touch and recompile Renode. And yeah, for kind of enabling practical scenarios, we have quite a lot of integrations. Here's a like selected list. It's not everything, but they range from stuff used for continuous integration, which is of course a major focus, and I'll have a whole segment of this presentation about that. To things that and like GDB. Through GDB, we can integrate with like any IDE, right, that uses GDB as the method to communicate with hardware, because essentially we're virtual hardware. So you just the IDE will think that it's talking to real hardware. It's really talking to the simulator. We have simulator with Verilator. I'll tell a few words about it later. It's pretty cool because you can do co-simulation of real physical hardware. USB IP is some interesting thing too. Like you can talk to USB devices from Renode. We do have like support for stacks like USB, Ethernet, and all sorts of things where we can do also like host guest networking, connect physical devices to simulation. There's quite a bunch of interesting things we've done in that area. And then there's tools like Wireshark that just enable you to debug and test things more effectively. And of course, we could theoretically re-implement Wireshark, but in practice, of course, it doesn't make any sense. So we want to integrate with those kind of tools pretty neatly. So if you want to kind of read up a few things, I've put a bunch of links there. We have notes about different things like integration with Verilator or Platform IO. Actually, it wasn't on the list in the last slide. It's a mistake. I should put it there. It's a really cool thing done by Carlos Eduardo from Red Hat. And he put together a note on the Linux Foundation blog about that. Well, not Linux Foundation, actually, Zephyr project blog, right? That's a mistake. Kate knows something about this. I think that's one of the cooler things out there, because indeed, if you grab Platform IO and just run 2 commands, you're going to get Renode running that specific platform. So yeah, if you want a shout out for Zephyr, I can do multiple because we support Zephyr quite a lot. So for example, there's this other node for TensorFlow Lite support, which we did with Google. And we integrated TensorFlow Lite with Zephyr, and we've done all that in Renode, of course, and on real hardware. I'll show you an example, or rather this repo that contains that sample. I'll tell you a little bit about it later in the presentation. But yeah, it's kind of, there's a lot of Zephyr in this presentation because it's our default RTOS. That doesn't mean we are kind of bound to Zephyr. We can simulate other stuff if that's your thing. We're completely neutral, both as a company and as a framework. But I think that kind of even strengthens the claim of Zephyr, because we choose Zephyr for a lot of stuff we do, right? So we choose it not because we're forced to choose it. Someone told us to. We choose it because we like it, and we use it quite a lot. There's a bunch of other interesting things that people have put together. Like Menfold did this blog note about using Renode for CI using GitHub Actions. It's a pretty detailed overview of how to do that. It's a really good read. And generally speaking, we can kind of test protocols and different stacks. And I've just listed some of the things that people have been doing using Renode. Most recently, OPC UA implementation for Zephyr is being tested in Renode, which is a pretty cool thing. We managed to, kind of stumble upon Sisterel that's doing that at Embedded World this year, tell them how great Renode is, and, get them to use it. And now we're collaborating around that. So there's a pretty nice, amount of stories behind this. I'm not going to give you all of them because it'd be a very long presentation, but we can see that a lot of people are starting to use Renode in contexts that we wouldn't necessarily have figured out ourselves, that are even possible. So hopefully the links I gave here will be a useful read. Since it's Linux Plumbers, I thought, okay, we need to say what kind of Linux stuff can run in Renode, because even though microcontrollers are a big focus, we want to enable a lot of like IoT focused use cases. There's no IoT without Linux, and we run Linux on RISC-V, ARM, and Power. Some of the platforms that that's a shout out to Drew, that obviously the most important thing you're going to do in Renode is view penguins on the screen. I think that's actually the tweet that I'm showing here. So yeah, viewing penguins on the computer without hardware is very, very useful. That's kind of the primary functionality of Renode, of course. And we have a bunch of like Linux-capable platforms. As you can see, there's a heavy representation of RISC-V because that's been our major focus recently. But there's also ARM platforms on which we can run Linux. And there is nothing that's blocking Renode from supporting more ARM-oriented platforms and like Linux-capable ARM platforms. It's more a matter of where our focus has been based on customers and requests and so on. So we support a lot of those microcontroller devices because that's what is not really well supported in other places. But there's nothing stopping you from implementing more Linux-capable platforms. These are the ones that you can run today. I just wanted to give a shout out to some very interesting. No, I'm sorry about BeagleBone Black is not supported yet, but yeah, it should be, of course. So Vex RISC-V is an FPGA implementation of RISC-V. It's actually the best FPGA implementation because it's kind of high performance but pretty kind of low resource usage thing. It's very scalable. You can go from like a small lattice size 40 to a big FPGA. You can run it in multi-core, so you can run 4 cores in an FPGA running Linux. And it's the winner of the 2018 RISC-V soft CPU contest, and for a reason. I mean, it really did very well, and since then it's been improved greatly. We had the pleasure of working with the creator of Vex RISC-V, Charles Papon, and he's a great guy to work with. We've been kind of working with him to add this multi-core capability and other features into Vex. And generally speaking, we work with Vex RISC-V a lot because we do a lot of work in FPGA. And this is just the single most, I guess, flexible and useful RISC-V implementation out there if you're doing FPGAs. And we support a lot of the peripherals that people typically use with Vex. I'm not saying this here, but Litex is an SoC generator that's very often being used with Vex. And Litex has a lot of IOs like Ethernet and UARTs and SPI and so on. All of these peripherals are, or like the vast majority of those peripherals are supported in Renode, so that if you want to prototype something with Litex and Vex, you just can grab Renode and run this. And that includes both like Zephyr, bare metal Linux. Vex is very flexible, so is Renode. So that's kind of a very useful platform and ecosystem if you want to do FPGA stuff. Another kind of shout out to Linux capable RISC-V platforms is PolarFire SoC. It's a really great development, first mass produced Linux capable RISC-V. We're very early adopters of it. I mean, not just because we love RISC-V, but we're also actually a partner of Microchips, and we've been helping them to support it, to support this platform in Renode. Microchip has been running a series of presentations and webinars about Renode and about their platform. So essentially, they gave us, before the world even knew about this platform, they gave us all the, data sheets and everything for the platform. And we created support for that platform that's very comprehensive. It includes all the peripherals in there. So people that wanted to test that platform before it was available could use Renode. And of course, we want to encourage them to continue using Renode for this, even though the platform is starting to be available physically. So like this is the Icicle kit that they just released. I think the general availability is kind of happening very, very soon. We have this board, of course, because we're a partner, but soon they should start shipping this board. I think it's $500. It's not the cheapest, but it's relatively kind of well available, and and comes with Renode. So what's not to like? And if you want to simulate that board today, right now, just kind of download Renode. I'll show you where to get it, and you can just run a demo, and that's what you're going to see. You're going to see the Renode console, you're going to see a log, and you're going to see, well, the console from the actual device. And basically, that's how you do it. You go to the Renode documentation, and in this documentation, there's a support board section. You use this command inside Renode to run whatever script that didn't fit on the screen here, but right before the name of the board, below the name of the board, there's a script name that they have to run this demo, the demo that I showed on the previous slide. Okay, so that's about Linux. I think that since this is an IoT session, I'll switch over to like networking IoT. As I mentioned, the multi-node capability is kind of a very big use case for us, and the fact that we're also a deterministic framework opens up a lot of IoT use cases. We even have like a simple networking medium simulation, so we can do things like distance-based packet loss if you're doing communication wirelessly. And of course, it doesn't mean that we simulate like physical stuff, really, right? It's still a virtual, like digital simulator. But of course, like distance-based packet loss is very useful, because if your packets are not arriving, it's very easy to see whether your protocol is ready to handle that. And the reason is kind of like, you don't care what the reason is. The packets just didn't arrive. What does this software do when that happens? So even though the simulation of the wireless phenomenon is really, really simple, the actual kind of results for testing capabilities are pretty huge and interesting. And of course, what people have been doing is testing protocols and stacks on top of it. And also kind of course, we don't necessarily want to re-implement all sorts of like wireless testing frameworks. So we have Wireshark. There's someone actually working on Whitefield support, which is like a network simulator for Renode 2. So like we're very happy to kind of work together with external frameworks for wireless testing to enable this. And so that's what you're going to see if you try to run like a Wireshark demo in Renode. So to the right, you can see Wireshark, and there's some kind of TCP communication. I think it's actually Ripple UDP communication going on here. And just looking here, I think that is that. So there's a server, there's a client, they're talking, and Wireshark doesn't really know that the packets are completely virtual. They're not.
There's a DODEC, so that's Ripple, yeah.
So kind of Wireshark doesn't know that these are fake nodes, these are simulated nodes, and it just gives you like a protocol analyzer for IPv6. So that's kind of pretty cool. Yeah, and if you kind of think about this context, like then continuous integration becomes an obvious thought that comes to your mind, like how to kind of encapsulate this complexity. Well, you put it on a server, you make it compile automatically, you make it kind of test every comment of what you do. And we, of course, do that even for single node systems, but for multi-node systems, that becomes like a superpower. And basically, we use containerization a lot, of course. We use Docker, we use Singularity. It's very important if you're working with so many firmwares that we are, like, since we're running all those kind of different firmwares, running in Renode, different versions of Renode, different versions of firmwares, different boards. Containers are a big, thing you need to do. Yeah, there's a lot of stuff that's good about CI. I don't have to, really convince you, but like just think about it in the context of people developing IoT devices. If you're building multiple product variants, you're building like product lines, and all of these might be running different firmwares in different times and at different sites. Encapsulating this complexity into simulation and CI is extremely useful. It doesn't feel like it's very useful like initially when you're just developing the first thing on your table, right? You have this one device on your table, it's working, so what's the problem? But as soon as you start kind of deploying that and kind of working in a context of a real system where there's so many use cases and so many problems that could appear, doing kind of testing with Renode is going to be really, really necessary. And that's what we envision kind of a typical CI flow to be. And the important thing for us is that you can also use Renode as an interactive tool on your desktop. It's not just for CI. It's, of course, very important, but we want people to be working like interactively and kind of debugging and testing stuff on their own computer. And the CI setup that's kind of in the company environment is like something that you then plug into as an individual developer that gives you the ability to also kind of communicate to your colleagues and work together in a team. So we'd envision everyone in a team to have Renode installed locally and then also Renode to run on a server. Kind of, I assume this kind of diagram is not really unknown to you if you're in software development. The challenge is this kind of diagram is pretty much unknown to many people in the IoT space or embedded systems space because it's very hard to achieve this with physical hardware. If you have physical hardware on a table, your colleague doesn't necessarily have the exact same board. They might have resoldered something or connected it differently. And your server room doesn't have that board typically. So kind of this reproducibility aspect is super important here. So yeah, as kind of, I'll be talking about Renode robot integration in a second, just to illustrate the kind of types of firmwares we've been working with, and that's not even a complete list. There's a great deal of like real-time operating systems. There's Linux. There's MicroPython. There's Android, there's bare metal, bootloaders, and this is just listing like mostly operating systems really. If you go to like protocols and stacks, the list grows exponentially. And we're very happy if people kind of come to us and say, oh, I've been running, I don't think SL4 is listed here, but for example, some people have been running SL4 in Renode and actually porting SL4 to RISC-V using Renode. So that list kind of grows on its own. We don't even have to do anything. Okay, so this example I promised, I think it's really useful to take a look at this. This is a TensorFlow Lite demo we did for Vectors 5 in LiteX on Zephyr, of course. And there's a bunch of files here, so I'll try to show those files. So first is actually a peripheral that we implemented specifically for this demo, which is an I2C. And since that I2C did not, at that time, exist in Renode, it's now in the main line, but it wasn't then, we actually included it as a separate file. And you can compile stuff on the fly and add it to your existing Renode installation without actually, well, it compiles on the fly during the run of Renode. You don't have to do any like compilation. You don't even know how to compile Renode to use this kind of file. You just put it in a project and it's going to work. And since we have a lot of useful abstractions and it's an object-oriented programming thing, this I2C implementation isn't necessarily very long because we can leverage the fact that most I2C devices look very similarly, and we just have to implement a bunch of functions. So this file is actually a separate Renode peripheral that just gets plugged into the framework seamlessly. All right, 5 minutes. Then there's some data files. So since these are like sensors that we're testing here in CI, we have some synthetic data that we can kind of supply to Renode from a file. And this data is going to give you a circle or an angle pattern, and those patterns will be detected by TensorFlow Lite. And you're gonna, it's a little deep learning, deep neural network. I mean, it's okay, not really deep, right, at this point, but it's a neural network that takes this data and sees patterns in it. And you can already see how putting this data in a file gives you a reproducible, like you can work on your neural net layout, you can work on TensorFlow as a framework, you can work on your operating system, you can work on your sensor driver code, and you change them, and if you break something, you're going to see that this angle or this circle is no longer being detected. And it's always the same data, right? It's very hard to do physically if you have a physical board and you try to kind of, okay, let's see if this circle pattern works. You're going to be like waving your hand around, and you'll never do it the same way, right? Versus synthetic data, of course, is going to be always the same. And you can, of course, think about how you randomize that data a little bit and generate, lots of different test cases. Then there's a REPL file, which is this Renode platform file that I showed. This puts together the platform from building blocks. So it's a very important file there. Resc is a Renode script, so that's the script that puts the binary on the platform, and you could enter those commands interactively in Renode, but normally we put it in a script so that you don't have to do it all the time. And then there's a robot file, and that's kind of also interesting. And robot gives us an ability to nicely put together test cases in similar to natural language, where the tests also give you a nice report that shows how the test went and what went wrong and when and how long things took and so on. I'll show you that in a second. Here's an example. So the test is on the left. The console results of the test are here. And then the report that's generated, this is kind of a little bit spiced up with Renode branding because the report normally looks a bit worse. That report that we generate is kind of gives you a detailed overview of the steps taken and so on. And we actually generate a lot of these kind of test pipelines. So I'm just showing you here a screen of something we're building. This is going to be a public kind of list of things that we build with the latest build results and artifacts for various platforms and various use cases. We just need to kind of put it out there and include more of the test cases that we have running internally and expose them to the external world. But you can see that there's kind of coverage of various platforms, protocols, operating systems, and we want to enable all that and show people how to do this. If you're interested, just go and download Renode. There's packages for various Linux-based systems, but also Mac and Windows. We do support all the major operating systems. And we've recently released 1.10. I think one interesting thing to mention is we have a portable Renode installation option. So you can kind of just download a tarball of Renode, unpack it, and it's going to work without dependencies. And there's also a bunch of stuff that, fortunately, I'm almost finished. There's also a bunch of stuff that we added recently, different kinds of platforms and so on. And yeah, just to mention, if you kind of want to do stuff using Renode and you don't know how and you want help, we do offer professional support, and we build embedded systems, we build CI systems and tools. So you can always hire us to do that. That's it. Managed to fit in the timeline. Yay.
Thanks, Michael. That's pretty fantastic. I'm pretty excited. I'd like to try out Renode at some point. Did you say you had a quick video to share as well?
Oh, right. I forgot about that. I have that video. How do I put the link in? How do I?
The plus button at the bottom left. You should be able to share the video that way.
Okay. Yes. It's a short one, unfortunately. This is running this triple UDP example in Renode. That's what a normal run would look like. You can see several UART windows being opened. And here we're actually showing some of the wireless capability where we're setting the radio distance, to be shorter, shorter than the position, the kind of displacement between the nodes. And then the packets stop getting through. And then once we actually move, so here's the nodes are 10 meters apart, and then we set the range to 9. Packets suddenly stop getting through. There's a request, there's no response. Now we move one of the nodes back into range, and suddenly we can see that there's some packets that are getting through. It's of course a very simple setup, but you could imagine that scaling to many nodes where these kind of things are really difficult to catch, and this kind of automation really helps. And of course, this is interactive, but in reality, normally you'd probably run that in Robot or some other test framework. Yeah, that's the whole video. There's nothing more.
Do we have some time? I think we might have a couple of minutes for Q&A. Does anybody have any questions or?
Yeah, well, I've got a question if no one else does. Are there things that should be looked at improving in the interactions of the Linux kernel and these simulators so that more capabilities can be added? Are you running into any boundaries on the Linux side or things that are impacting your ability to do the simulations?
Not really. I'm not sure, kind of probably there are things that could be improved, but since Linux is just a type of software you can run, we don't necessarily, even if, we sometimes do leverage the fact that you can kind of cheat and implement something for a specific, OS, and we've been thinking about OS awareness kind of stuff. The funny thing is we don't really need that thing because, say, we can do tracing without instrumentation, right? We don't actually need to put stuff in the code because we execute the code ourselves. So we can kind of guess what's going on by just looking at the code from outside. And I'm sure that if you kind of implemented specific stuff to enable these kind of things inside Linux or Zephyr, you could get even better results, but you can get very good results without actually doing anything. So that has been our approach so far.
Okay. I think Chris is asking about KVM and libvirt with the question marks in the chat.
Super
yeah,
cool
that was
question.
just kind of to your points about possibly accelerating things on the Linux side or on the simulator side.
Yeah, we've been, of course, looking at KVM libvirt. We assume that QEMU does these things really well, so kind of we didn't, spend a lot of time addressing that specific issue, because if you want to virtualize things, QEMU is a thing. But in reality, of course, we do think that Renode has this kind of possibility to play a role in that space too, and we'd love to enable that too. We don't see a reason why Renode shouldn't be able to do that. But currently, we can actually run x86, right? We do have support for x86. From the time when Intel was actually doing IoT nodes based on x86, Galileo times, we implemented x86. But right now, it's kind of not a major focus.
Okay, we're just a couple of minutes over. I'm going to do a last call. Does anyone else have questions that they'd like to pose to Michael?
I guess one thing I just wanted to maybe clarify was what the difference is between QEMU and Renode is, because sometimes I get asked that question. And my understanding is that it was at one point based on it, but it's expanded beyond that. Is that correct?
I mean, yeah, people always like to poke us and say, "Hey, how do you compare to QEMU?" I guess the thing is, there's room for both solutions. Our focus is more on this kind of complex system, multi-node aspect, and simulating entire systems with complex I/O. And QEMU is typically more around the architecture itself and the CPU itself, virtualization, which is a huge focus, and we're not there really. And there's a certain amount of things that overlap, like you can actually do the same thing with QEMU and Renode. But I think the fact that we focus on determinism, is something that you won't get with QEMU. on purpose, right? Because they want to be as fast as possible. So kind of you skip determinism and you just kind of go as fast as you can. Whereas, I mean, for us, for the testing concept, determinism is kind of mandatory. It's actually, you can turn it off, right? So it's not really it's not really required. You can run Renode in non-deterministic mode, but like, of course, if you really want to do serious testing, typically you kind of like this determinism because you want to show your colleague, hey, this is not working for me, and you want the same thing not to work for them as well.
Okay, thank you.
Thanks.
All right. Well, thanks again, Michael. That was a fantastic presentation. I think we're actually just running a little bit behind, but I'm gonna set Stefan Schmidt up to go next. So Stefan, let me just get you the presenter. And there you go.
So everybody can hear me? Okay, great. Let me check here. Okay, great. So first of all, big thanks to all the organizers of Linux Plumbers and the micro conference here. It's my third virtual conference I have over the last 2 months or so, and I have to say this one is by far the best organized one, especially the big blue button system is working out quite well, I find, compared to something like just having a big Zoom call or having like a virtual experience bought by some provider for that. So I'm just going to say I'm really happy with it. So, and pulling something like this off in this kind of time frame was really amazing. Okay. So I don't have any videos or any demos or something. I'm feeling a bit old school right now, but I think that's it. So let's get started here. So I will give you a short update on what has happened in the 15.4 space and a special thing about RippleD, which we just started in the Linux WPen project. So the background for myself, I'm a FOSS developer since like almost 15 years by now. I'm an EFL developer and release manager, but I'm also the Linux kernel subsystem maintainer for the 15.4 subsystem, which is mainly the reason I'm here and talking. So for the agenda, I will just, when we set up this micro conference, I was thinking I have like 10 or 15 minutes to give status updates, and then I found out we have like a full 40 minutes time slot. So I was thinking that I put in some more information about IPv version 6 over LowPan as a motivation. I mean, we had some of these already in the thread talk, so I might go a bit faster here in the beginning. But then I will go to the Linux WPen project and a bit more about RippleD, which we just worked on. Okay, so what kind of products are driving these 6LoWPAN stuff, for example? So we have like the basic notion for 6LoWPAN would be having IP version 6, the protocol over 15.4 as a physical layer. That has changed a bit over time, so there are different adaptations for 6LoWPAN by now, but that is a basic idea. But it's also quite similar to the newer Zigbee profiles. So the new Zigbee application profiles are running over 6LoWPAN as well. And then, as described before, OpenThread is also using 6LoWPAN on the lower levels. So the kind of product we're having out there in the market already, because that is kind of a motivation for people to look into or build something similar or basing it off on there. So all the Nest devices, the thermostat, Protect, and all the newer stuff they are now releasing since acquired by Google are based on the Thread protocol. And so they're using 6LoWPAN. Then there's the Google Wi-Fi and on-hub routers, which had 15.4 transceivers in the hardware. I don't know if they're enabled yet or not, but they're available. One of the new things is the IKEA thread tree system, which is a bit of a hybrid approach. So on the 15.4 side, you have Zigbee Lightning protocol, and then the application gateway you have, that one you can access with newer things like co-op and other protocols, having like an application to talk to that. But on the 15.4 side, that's plain Zigbee. Same with the Philips Hue system, and there are many more available for that. So why would you go a route to having like a full IP protocol over something like 15.4? Before 6LoWPAN was a thing, there have been tons of stacks which have been just using their own homebrewed protocols, making sure that they make best use of these small MTU sizes you have with 15.4. But over time, there has become a realization that while you have a restricted wireless connectivity, you still want to use existing and proven protocols. For example, the ones driving the internet. But there are problems, obviously, with that. So it was designed for something like Ethernet with 1,500 bytes per MTU, but that's very different for 15.4 where we only have like 127. So there's a problem with having things like the TCP/IP protocol header itself being quite big, and other parts of the protocol really clashing with the MTU limitations you have. Luckily, on the other hand, you often only have to transfer small amounts of data for these kind of things. If there are sensors for like a temperature amount or just a movement from an acceleration sensor or something. So what is the 15.4 specification coming in here? So it's quite old. It was designed as low-rate wireless personal area networks. By now, the personal area has been scraped from the idea of the standard by now. But it's not only low rate, but it's also low power. So the PHY and MAC layer, which are defined in the IEEE standard, only allow for star and peer-to-peer topologies. If you want anything like mesh on something like that, you would have to run that on top of that. There's also no addressing, there's addressing defined, but no routing. And they're really designed for having something like a small sensor running for months or years on a really small like coin cell battery. That is like an amazing thing to do, so that's quite interesting here. But as I said, it's low rate, so it's like 127 bytes and only like 250 kilobit. That was the initial specification. It has changed since then, so there are amendments where you can have like bigger MTU sizes or faster rates or something like that. It also changed to not being in the 2.4 band only, but also going to sub-gigahertz by now. So it's more complex by now. Yeah, so the relation with ZigBee is often people mix that together. It's that ZigBee is using these PHY and MAC layer, but having their own stuff on top of that. And compared to Bluetooth Low Energy, for example, it's less complex to that, and it's older than that. Yeah, that's basically the background here. So if you look at it, what 6LoWPAN add to that? You have the physical MAC layer defined already, and then the IETF sat together and wanted to see what they need to do or what they can do to adapt IP version 6 on top of that. That resulted in a series of RFCs over time, starting in 2007, but still going on. And I think over the last years there haven't been much things going on there, but it took a while to get that all sorted out. So the basic idea was to have like a sensor or something like that directly addressable in a network over 15.4. So you have direct IP addressing for nodes. That is kind of very different to other approaches we have seen before, where you had like the gateway, which has been kind of a proxy to map between the different systems and between the different nodes in the different networks. So to do that, we have an adaptation layer between the data link and the networking layer. If you look at the OZ model on the bottom there, you can see that where you normally would have like only IP, you would have like IP version 6 and 6LoWPAN merged together in here. It basically offers address auto-configuration, frame encapsulation, and fragmentation, which is really important because the MTU size is very different. And also for that, you have header compression to make sure that you make best use of the MTU size you have. And that brings me to the header size problem. So if you would go really naive at these and say, okay, I want to run IP version 6 over 15.4. Then you would go ahead and say, okay, you have like 127 bytes. Say you have take away the maximum frame header of 15.4, which would be 25 bytes. Then you go and say, I want link layer security in 15.4, make sure everything is fine, encrypted and authenticated. That's another 21 bytes. And then you go and put a full IP version 6 header in there with like the addresses and stuff like that. So that's 40 bytes. And then another 8 bytes for UDP, which means in total you have like 33 bytes left over for payload in one frame. That's for every frame you're transmitting, right? The ratio is quite heavily towards the headers in contrast to the payload here, 3:1. So it can work, and you can do that if you know that your payload is really small, or if you don't care and are fine with stretching it over different frames or something, but it's not really efficient. What you can do is, like, a lot of these things are known in these kind of systems, and you can reuse parts of it. So if you go and say you have like an IPv6 link local communication with UDP on top, which is a common scenario, because most of the time UDP, not most of the time, but often UDP is used because you don't have the delays with a handshake initially and so on. And with UDP and DTLS, you have encryption as well on that level, so that's nice. And then you have things like IP header compression and max header compression for UDP. I will go into that a bit more later. And that means the 48 bytes you would normally have for these headers could be reduced to something like 6 bytes. That would be really nice to have, because that means you have like a payload of 75 bytes left over for real data you want to transfer per packet. That means frame header and link level security are still the same. You just reduce the headers for the rest. Doing that mostly comes from using the layer 2 addresses, reusing them again in IP version 6, in IP for version 6, and leading a lot of the parts of the protocol header that are known and you don't need to change or something. It's still flexible to do that, but the best case would be to bring it down to 6 bytes, which is quite nice. Okay, so why did we start the Linux W pen project for that? I mean, you would think about that like that is something for out of systems, for really tiny devices you want to do that. But you still need kind of a border router. And Linux is going into smaller systems. So that is quite interesting for us to also look into that. I initially got in touch with that during my diploma thesis, like, whatever, 9 years ago or something like that. And we had like a small wireless sensor networks we are working with. And one of the nodes we have been running there, even on battery, was a Linux-based node. And we had like 15.4 transceiver, and we wanted to transfer data over it. So that was where I got started to look into that a bit more. The idea was, or it still is, to get 15.4 and 6LoWPAN support into mainline. We reached that to some point by now. We wanted to have all the platforms that running Linux right now or would run in the future would have the benefit to just enable that in a configure option during building the kernel. And with an instant, you could have native 15.4 systems with 6LoWPAN. One point is that it's really easy to add them to your embedded board. The transceivers are so simple, you normally only need like a SPI interface and a few GPIOs for like IRQ and maybe some reset lines or something like that. So it's really simple to add there. On the other hand, you would have like battery-powered sensors which you want to run for like months or years or something. It's more likely to have a real RTOS, something like Riot, Contiki, Zephyr, or whatever you want to use there. So in 2008, this was started as Linux Zigbee, which was a bit of a misnomer because there was never real Zigbee work on it. I think that was an Siemens research and development projects at some point, and then in 2012 we finally got it over to get into the mainline kernel and renamed it for more clarity. So we have our development boards are mostly based on just having a simple thing like the Raspberry Pi or maybe even a BeagleBoard or something like that, and then just connecting a board with a transceiver over SPI and maybe some GPIOs or something. There are also some for the Raspberry Pi. There's a head to have that. There's also the CI creator board, which is based on MIPS. They already have 15.4 transceiver on the board, which is quite nice. And we also have the AT-USB dongle, which is really convenient for development purposes. Yes. So if you look at it, how would you bring that up? So if you have a kernel which has all these things enabled and have a transceiver connected, which is set up correctly, normally the WPAN 0 interface would show up automatically. Then you would go and configure it for specifics of your network you have, like the PAN ID, excuse me, the channel and all these kind of things. And then you would go and set up the device again, and then you could add a low PAN 0 device on top of that. And on this interface, you would then have normal IPv6 connectivity. Just to make sure, I'm not really looking into the chat, so if anybody wants to ask a question or something, just pop in here and then I can break, but I'm not really focused on seeing the threads there. If you want to have like a monitor interface or something, you can do that as well. You can just bring it up as a monitor type and then look at it with Wireshark or whatever. So there's no automatic channel hopping or something. Below that, the protocol is the standard is really simple there, but you can do the channel hopping in the background manually if you want. Okay, so the socket interface as well. As I said, if you go to the low PAN 0 interface, it would be a simple, normal IPv6 socket. You would do the same thing. You would use it like with every other IPv6 socket. So that is the idea, to be really transparent. Everything below is handled directly in the kernel level. All the header compression and decompression and all these kind of things are not visible to the user, so they can simply use a normal application and an IPv6 socket. But we also offer a 15.4 socket, basically, with an 15.4 address family to allow direct communication on that level. We have short and extended addressing schemes, as well as handling the network PAN ID and channels and so on. There's an example code below here. You can see how you would set something up. I mean, that's not running code, that's just some examples. If you're known to socket programming, it's quite simple to do, actually. So what is our current status? We have 6 low PAN with fragmentation and reassembly in the main line. We have header compression with IP header compression, next header compression for UDP in mainline that is shared with a Bluetooth subsystem, which is also using that for the Bluetooth IP protocol. And we have a 15.4 layer with a softmac for various drivers, various files we have around there. We have a hardware sim, which is a hardware simulating driver for testing purposes, which is kind of similar to the wireless sim driver in the kernel. We have a USB dongle, which is convenient to work on a normal developer station. We have something like links layer security, which is still very hard to use. I mean, it's only the lower level plumbing bits we have there. There's no whole concept like Thread has, like this key rollover, installing the keys, making sure everything works or so. We only have the bits where you would like put in the keys and make sure that everything is encrypted on the air and then decrypted on the other side. So there's a lot of work to do to make that really working. We just recently put some effort in bringing a new website up because the old one was really hard for us to use, difficult to maintain and access. So now I switched over to GitHub Pages. It's a lot easier for us. Just a Git repo, doing the edits is easy and so on. We moved over the content. We still obviously need to do more, which is not a surprise for any open source project, I guess. And we need better integration with the docs we have on the kernel side as well. So one of these things that recently came up, triggered by Chris, but also by other people, is people wanted to have like a way with a generic driver for an USB dongle. This has like 15.4 capabilities. That's something that has been in my mind for a long time. And actually someone at Intel started working on that a few years back, actually, but never really came to the stage where it was finished and ready to merge mainline or something. It was a good start and still is, but it's stalled at some point, I think in 2018 or something. So the idea was to have a Zephyr device with a Zephyr RTOS and then have an application on Zephyr which would expose a specific USB interface as kind of a host controller interface. And then on the Linux side, you would have a driver implementing this protocol as well and using that. It's kind of similar to what Bluetooth actually describes in their specification. It's just that 15.4 does not have that at all. So they don't describe any host controller interface. Yeah, they started with using AT-USB or dongle there, and the USB interface for that, and then stripped away the things that are hardware specific and try to be a bit more agnostic, generic, and started to put together a Zephyr firmware to make that working, as well as a kernel module. So that's something that was started but never finished. But people got more interested in that again recently, so we started to look a bit more into it. So there's Kuhn, as a developer from the Riot auto system. There's Eric, I think, who's with Beagleboard fame. I'm not sure about that. And myself, I'm also interested in looking at. The idea is to extend the interface we have, the spec. Oh, Jason, go ahead.
Yeah, just so yeah, Eric is working on it for us to try to do the USB connection, and so understanding what the good options are to go from USB. I think there's unfortunately I'm probably not the right person to ask the question, right? But it's so do we think that WPAN USB is kind of going to be the one to handle the connections to the radio for border routers? You know, because I think there's something else that's in there today that's popular. Yeah, I don't think I'm the right person to ask the question, but
No worries.
if you can give us just a little bit more on this one in terms of what the alternatives are and how definitive WPAN USB is, it'd be helpful.
Okay, no problem. So the idea is, I think most people involved agree that that is the first way forward. I mean, we might need to reiterate and define it a bit better later on, but the idea is to take the USB spec that is already developed by the Zephyr people from Intel and make it a bit more flexible. So having like during probe time, we would like to understand what kind of capabilities the firmware would provide, what kind of different frequency bands the hardware, the transceiver would offer, what kind of power levels, the permanent address from the board, and all kind of other things, which is quite important because if you have like a whole auto system on the other side, which a variety of boards that it can run on and a variety of transceivers it could operate on, it would be really good to have that like on the probe phase to actually understand that and then set the right things in the kernel driver. My understanding would be that you then would have like a communication interface from Linux to have like these Atlas board as just as a normal external receiver, transceiver basically. So there's no other things involved.
I'll let you know one of our challenges is that the microcontroller that we're using for the 802.15.4 doesn't have USB interface on it. So we're putting a small microcontroller in between that's currently just doing a USB to UART bridge. And so that's the kind of approach that we're taking. So we're essentially doing UART instead of a native USB protocol.
Okay. Yeah, we had that. There was a specification for something like that. So having like a transceiver over UART, there was a spec for that as well. I never really looked much into that, but having UART as a protocol transport might be possible as well. I'm not sure if we really would want to fit that into WPAN USB. I would prefer to have that like a clear USB interface spec and having like a different way to do that. But yeah, UART has been requested before, but nobody is really looking into that much. So we might need to have like a different approach on that as well. Okay, so we had like 2 weeks ago, we had the NetDev conference where I was sharing the IoT networking protocols workshop. And the CAN subsystem maintainers, when they did like their status report and talking about where they're going, we then found out that they have kind of similar needs for that. So it's like for developers for getting something ramped up or so, that's quite interesting to have this kind of functionality. And we will see if we find a way to actually work on some pieces for that together. Obviously, the interface would be quite targeted to what kind of protocol we were operating for, but some of the more generic pieces could maybe be shared or something. So there was interest from their side as well. Yeah, the idea was that Kuhn was looking into developing Riot as firmware for that, and we would need to find out if we can update the Zephyr firmware as well. Something I also was interested if anybody wants to have like a bare metal or Contiki implementation, but I think that's really driven by need. So if anybody shows up and wants to have that, it could be done, but that's not really on my agenda or if anybody else involved there. Yeah, then you have like KE self-test support, which is something that gets a bit more important because FIFNet was not so heavily developed. I mean, we are only like 2 people doing it on our spare time, basically. So it's not like we are catching up with all the major changes in the networking stack. So we had one situation where there was a major rework of the TCP/IP stack, which also touched on the 6LoWPAN work. And that led us with a broken system for a while because, yeah, it was really specific. And the thing is, the original committer had no way to test that. So we wanted to find a way to actually automate that in case self-test using the hardware simulation driver and finding a way to allow these kind of things running, which I also can then use during the review process. But that's still ongoing work. I have a branch locally looking into that, but it's not progressing that fast. Yeah, that brings us to the future. So what is on our agenda? This kind of slide is sadly looking quite similar to what I have been presenting, I think like 2019 or something. So there's not much progress made over the last year, I have to say, which is sad, but also reality. There are missing parts in the 15.4 specification we are not having implemented yet. Something like beacon and MAC command frame support, which is mainly because we don't really use it. So for 6LoWPAN, you don't need it for just data transfer. So Chris, go ahead.
Oh, I was just going to say, Michael Magyar, who presented earlier, and I, we were colleagues at our previous employer. It seems like a lifetime ago. But Michael and I and a couple of other colleagues actually did all of the beacon MAC stuff and scanning that you're talking about. And so we were just chatting there and saying that we're going to both look through our archives and try and piece together everything, because it was
dust it up and send it in. So.
Yeah, we just need to get it done. So sorry to interrupt.
No, fine. That's I can happily. I'm cutting away slides or something for discussion. No worries about that. So yeah, as I said, so the main reason we are not having that is like because there was no need. So the normal data command frames, data frames we had have been enough for 6LoWPAN. Yeah, having this kind of support in WM tools and scanning and so on would also be needed. Something that's also a bit more urgent even, I would say, is like hard MAC transceiver support. So we have like the soft MAC, but we don't really have a good way to allow hard MAC transceivers to be in the system. We have one driver which is doing some nasty things to get hooked up into the soft MAC correctly. But that's really on our side to get that sorted out. But I haven't come around to actually do that. I still want to have a configuration interface for the various header compression modules. Right now, it's only enable or disable during the build and then loading or unloading. That's all we have. There's no other configuration scheme for that. Mostly because we feared a bit to implement a user space API where we are not 100% happy with because we couldn't change it afterwards. So that's something why we are not having done that yet. And we also need to gradually expose information needed for routing protocols. We started with AQI right now already, but we might need more later on. But that's something that can be done, but there would be a clear need for that. I don't want to expose things that are not used. So what kind of RTOS systems are kind of like working together with that? As I said, Riot, Contiki, Zephyr, OpenThread, even Embed OS, they have finally open sourced parts of the networking stack they had in the initial release or something that has been closed source, which was a bit of annoying. I think it's open source now as well. So there's a variety of RTOS systems available that could work together with that. We did some interop testing with some of them, but that's a while back. But in general, I would say that most of the problems should have been sorted out. Depending on the level of support we have, which is like a small comparison here. as you can see, like beaconing Mac command frames and scanning and joining is something that is not really, or maybe I'm not 100% sure if Riot has implemented by now, but it wasn't when I last looked, and that's also again because the data and ACK frames have been all you needed at that point. For OpenThread, that's a bit different because you need this kind of like joining a network and scanning for that. That's part of these thread specifications, so you need all these kind of pieces. So I think maybe the Riot and Zephyr application ports of OpenThread support that, but if it's a native network stack does it, I'm not sure right now. Thank you. Yeah, so that's, as you can see, that's not much to say about. One interesting thing here is generic header compression, which is an RFC, but hasn't been implemented anywhere. I have a local branch as well, but it's not finished yet. So, and I'm not even sure how really useful it is. Let's jump to RippleD, so because that's something interesting. So Ripple is like a routing protocol for low power and lossy networks. It's the IETF approach. It's defined in various RFCs over time, and it basically gives you a tree-like topology in a mesh with relation with one parent and childs. Excuse me. And it constructs a direct iFactory graph to get the routing costs down, basically. Yeah, if you look at that, you have like here a situation where, like on the left, you have like the mesh how you would look at it, and on the right side, that would be the routes for upwards and downwards. You can see like route 6 would be reached from route 1 by going to 2 and 5, obviously, and you would have to make a decision for 4 if you go over 2 or 3, but depending on like the network characteristics, the physical characteristics, like what the distance is, what the latency is, and so on. And, yeah. So RippleD is like the like one of the implementations, one of the kind of reference implementations called Unstrung, which has been developed by Michael, who's one of the was a share of the RippleD working group in IETF. But it was more like, yeah, just implementing and finding out if all the specs they are working on are actually working. So it's not like something you would deploy or something, I would say. So we started to look into RippleD as an alternative. So in the initial years of Linux WPen, we really don't want it to go into routing because we had our hands full with all the other things already. But over time, it really has become clear that routing was something people expected as well in the package to get anything running. So it's only around for a year or something. Alexander is working on that. And there was also like 2 weeks ago at NetDevConf, there was a talk about that in more detail. So if you want to look into that, that might be a good idea. There's a slide, there's also a paper, and the videos should be up within a few weeks or something, I would say. So the basic idea is that RippleD in non-storing mode. So there's 2 different modes RPL can operate on. Storing is like having like the routes propagated with ICMP version 6, and then these things stored in the routing table, which is a problem for really tiny devices with small amount of memory or something. So that's not always feasible. I mean, for the big Linux box as a router or something, that's not a problem, but for small things it might be. Then there's a non-storing mode where we would have like source routing with the routing header inserted into the packages itself, and then finding their way through these insertions of the routing header. And non-storing mode has not been implemented in any of the other Ripple implementations on Linux, as far as we know, because there's been missing kernel support for that. And Alexander just did all that work for that and extended the Linux kernel segment routing implementation to actually make sure that we can do non-storing mode on RippleD. All the patches he proposed have been merged a while back, and that is also part of the talk I mentioned before. So yeah, as I said, so the source routing extension header is only inserted by the root node. It's obviously IPv6 only because Ripple is IPv6 only as well. And then you have like all kind of things like the forwarding of addresses and swapping, the compression of addresses in the headers and so on. And details of the implementation are in the mentioned talk. So I need to speed up here because I guess I'm running out. Oh, actually it was the last slide. So Yeah, that was it from my side. So I'm open for questions now.
Hey, Stefan. I
Yeah.
had a really quick question in terms of the link layer security. So, I mean, it's been a while since I've been working with 15.4 on a day-to-day basis. But back then, I'm talking about 2015, not a lot of places were using the link layer security. And so I was curious, in your opinion, do you think it's effective, first of all? And I mean, do other encryption strategies possibly mitigate the need for it?
Yeah, so it is difficult because the 15.4 spec does not really define a good way how to handle that. They always say, well, that's up to the upper layers to do that. So it's not really comparable to something like Wi-Fi, where we would have like WPA 3 or 2 or whatever, and everything's like kind of specified and every client knows how to do that. So that's not possible with 15.4, which is a big drawback. And then the other thing is that it is quite huge in terms of frame eating, what kind of the MTU it's eating up. So if you really want to make sure everything is secured and encrypted, it's a good idea to do that. I still think it is, but then you would have to have like a controlled network and making sure that how the keys are rolled over, deployed, and so on, that is all under your control and specified at some point. So if you're, whatever, smart metering, or for example, small amounts of data being transferred or something, fitting in one frame or something, even with full link layer security, I would say go for it. And then you even might have space for having like DTLS on the UDP level as well. I think, but I might be corrected there, that OpenThread is also demanding link layer security. So it is, it has to be enabled to be like certificated and in that spec. So I'm not sure, but I think that's the case. So I think it's a good thing, but you have to find a way to actually make it work for your network, which means most of the time it's the network under your control. So if you don't care about that much and you really want to rely on what IP or other things on top of it offers you, I think DTLS is what you really would be looking into. And all the bits below would then be exposed on the wireless interface. And then you have to make a trade-off if you think that's a problem or not. Jason, you had a question? Yeah.
Yeah, I had a. I hope it is a fairly simple, unrelated question earlier about PAN ID. I'm just not familiar with you know, what's the vision for how PAN IDs are allocated within 802.15.4 world. It seems not just ad hoc, but just not. I mean, there's just no process. So, yeah, is there any thought around putting a process around defining PAN IDs so that you know, we can get on the right PAN? I mean, most of your networks, you just want everything there.
Yeah, I know. Right? I think it's more like it's just one small number, what number your network have. It's not like a full name like on Wi-Fi SSID or something. It's really just a small number. Even the thread network name, as an example here, is just a mapping. I mean, it's not like the PAN ID is just, I don't know how many bits it is, but it's really small. It just,
yeah, I think it's 16 bits, but there's not even like a back off mechanism. Like, how do you know to join one? I don't know if there's even a discovery mechanism, but how do you know to either join one that's active or back off? You know, which
the scanning, you can find things, but it doesn't mean how to really behave and how to interact there. So I think you can really go very far with just using the broadcast, like having FFFF, and be done with it. That could work, but honestly, I have no idea how they envisioned when they did the specification how that is used. I don't know how really relevant that is nowadays. So.
Yeah, because I'm just trying to, you know, if we just choose a random number for what we typically use for our devices, you know, is that good or bad, right? And I don't even know if it's good or bad to have these other devices on there. I mean, obviously it could be chewing some bandwidth, but you know, if we can have the same border router work, you know,
it's a bit of It's also similar to like how the channel allocation is working. I mean, you just randomly select a channel which you think is good in your environment.
But there's
right?
real performance differences in the channels.
Yes.
Like that's
Yes.
the crazy part. Like, how do we not define that in a really useful way, such that there is a process of defining what's going to have the best performance and choosing that, right?
I think Michael joined, and I think
need to solve
what
it.
he wants to say is that Thread offers something like that they have like kind of a radio thing. But I let Michael talk about that. I know that Thread had something like that, how you define these radio resources and to do that. Michael?
Your guess is slightly off. I'm not actually familiar with how Thread does this.
Oh, okay.
But it's instead, Zigbee has a pan-ID conflict resolution mechanism. And it's not just based on the 16-bit pan-ID, but the extended pan-ID that is 64 bits, that if memory serves is only shared during the joining and association process. So
But that is Zigbee specific, right? Because I never heard of a longer pan-ID.
The extended pan-ID? Don't quote me on this because it's been a while since I've been this deep, but I think the 802.15.4 MLME, some of the beacon primitives and the association request response primitives do support the extended pan-ID. So for us lazy humans, like everything you interact with Zigbee and with Thread is all using the short pan-ID. But the actual commissioning and joining process, if memory serves from Zigbee world, is based on the extended pan-ID. And then there was a mechanism that if there's a pan-ID conflict, for it to resolve and choose a new random pan-ID. But that was up to the coordinator when forming the network initially. I don't actually know how Thread deals with that for its self-healing and leader bouncing around aspects, but at least Zigbee has mechanisms to deal with that, and they were related to the extended pan-ID.
Okay, great, thanks. So I guess in the end it falls back to the coordinator of the network, right? It would be the instance who could go and scan for the existing networks and existing channel users and stuff like that, and then make a proper decision basically on whatever kind of decision-making process to use the right channel and the right pan-ID and something like that. And then the clients would
it would just be great if somebody would get down some best practices, just so that, as system implementers, we'd have some idea of good choices.
Yeah. So some of the branches that Chris and I were firing off in the chat from work that we did years ago was implementing active scanning, which would return back the pan IDs and the beacon responses, which I believe contained that information. So it would bring it into something in user space that could make that intelligent decision. This is again from years ago. I have to. This talk's inspiring me to go back and try to rebase that code on a modern kernel and get it running, because I remember us leaving it off as being very close to complete, and exposes a lot of this information necessary for beacon request, beacon response, active scan request response, and then the association request and response pairs, which would then get you an 802.15 for MAC layer association. And then what you do from there on network layer is up to whatever upper layer wants to deal with that.
That sounds terrific, actually. I mean, if you find the time and motivation to DDoS that, and then sending out the patches, even as a raw RFC or something, would be a great thing to start and look into that. I know it's on my list, but I never really had like the urge to do that because the use cases I had for it are covered. But I fully understand and agree that for a system integration perspective, all these kind of pieces are completely missing. So it's more like only for toying around right now. And with this kind of stuff around it, it would be way more feasible to do more complex scenarios with that. So I would be happy to look at these. So whenever you have motivation and time, I'm looking forward. Okay, so I think that's it from my side. No more questions. I need to catch up on all the chatter on the chat If there's anything left, I can comment there. So with that, I would go back to Chris, I guess.
Yeah, thanks very much, Stefan. So we've got just a 5-minute break, and then I'll be taking it from there. So be back in 5 minutes.
I'll just mention to those in the conference that there is a separate chat. If you go to the Linux Plumbers chat, there is a separate chat group for this micro conference if you want to do text chat, separate from the presentations.
Yeah, if you have, does anyone have a link? I think it was called Rocket Chat. I've not seen the link myself, but it would be handy to just post in the public chat area.
I'll post it shortly. Oh, looks like someone beat me to it. All good then. Thanks, Drew. Thanks, Jason.
And Rob did it too, so.
All good.
It has threading, which is kind of nice. It helps to keep things from being super confusing when people are responding.
Just gonna warm up the room a
I'll
little
just say,
bit.
since Frank is listening in, I might mention to him that we were discussing him in some of his proposal in the other room, so in that text chat room. So, Frank, you might actually join in there because there's some ask about the device tree sockets.
So who's got ideas for names for next year's microconference? That's my first question. Maybe I should make a poll about this. I've only got one suggestion though right now.
We have to use the poll at some point.
Okay, so my suggestion was IO3's company. That's all I got. I'm running out of puns here, you know.
Where are we supposed to be? If it happens, but it's Canada. I don't know. Maybe it should be themed Canadian if it's going to happen in Canada.
Okay, let's make a poll. Any other suggestions for next year? And it has to be punny. Pressure's on. So Drew, are you live tweeting everything?
I'm trying to do some. It's definitely easier with the virtual conference to tweet out stuff.
For sure.
It's all on the screen. The YouTube stream is great too. Like, I think that's probably the nicest thing about the virtual conference is it's all live on YouTube. You can go back and watch stuff again or miss the 5 other concurrent things, you know.
Yes, nice and also slightly terrifying. I have a major phobia of public speaking, but actually I find that this this format kind of helps with that. I know there are a lot of people out there that have anxiety with public speaking, so this to me is a lot easier than standing up in front of a large room and whatnot.
That's great to hear, actually.
I think it helps match our work style as well, since we're all used to working in our caves.
That's it, the cave, the safe zone.
Yeah. The water cooler effect, though, is still somewhat missing. I mean, I think we're all used to collaborating over chat channels and kind of creating a little bit of the water cooler effect, but I do look forward to when I actually get to see your faces, not through a LCD screen.
Okay, that's it. Break time is over. So I guess this is
Pressure's on now. Don't get nervous. Oh,
yeah.
sorry.
You're watching on YouTube? No, don't tell me. Don't tell me. Okay. Yeah, I'm actually quite pleased with the turnout this year. I guess we're starting a bit of a trend, which is good, right? Yeah, and thanks, first of all, to all of the presenters that came this year. And as a reminder, I'm hoping that everybody is able to stay just after my talk, and we'll do a little group photo just on just a screenshot. That's kind of a tradition that we started last year. So last year was the first IoT micro conference, and this is our second year, hence the name Yumi and IoT Two, just sort of a pun on the word two. Anyhow, I will get started. So yes, my name is Chris Fried. I have a background in embedded. I've been doing Linux embedded since 2005, approximately. I don't have a heck of a lot of patches upstream of the Linux kernel because, unfortunately, a lot of embedded companies don't push upstream. You know, I constantly encourage that. I think upstream first is a really great, really great policy. So I've been doing a little bit of work on my own under Fried Professional Engineering Services. Lots of great ideas. When Michael and I used to work together, we had one of our projects was to come up with a multi-node IoT simulator, much like Renode.io. So I'm glad that somebody made it happen. I never got the chance to. In any case, let me continue here. So how does this work? Next slide. Perfect. Are there keyboard? Oh, good. Okay. All right. So yes, this Internet of Things. What is it exactly? And according to the Wikipedia, it's a system of interrelated computing devices, mechanical and digital machines, provided with unique identifiers and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. So that is a pretty good definition. I would say it reaches all of the necessary criteria. And probably it might not include everything, but sometimes when we think of the IoT, we're usually just thinking about really small things. But to be fair, it also includes the very big things. Like that's why all of the major companies out there are trying to set up cloud services to back our IoT infrastructure, like Google, Amazon, Apple. So they want to sell our data back to us, which is a good business strategy. But in general, when we think of IoT, we think of the very small, very small. And as another generalization, the current IoT market is basically the smart home. Maybe I'll make a quick poll. How many people, let's see if, where do I even write this? Yeah, I don't even know where to write the information for the.
You already started the poll, so just ask the question, I guess.
Oh, okay. All right. So yeah, how many people have some IoT device in their house right now, like a smart home device of some kind, Nest, you know, Home, Alexa, anything? I'll leave this open for a little bit. So when we think of smart devices, IoT devices, we often think of the nice packaged, nice packaged products, but that's not always the case. And if you have a background working in 802.15.4 or Wi-Fi, or just embedded in general, when you look at these devices, you don't just really see consumer products, but you also see just devices. So when you're thinking of a smart speaker with some LEDs, it's you've got an audio subsystem, you've got a few GPIO. Sometimes you'll have some PWM LEDs, but for the most part, there are a lot of user-facing APIs that have existed for quite a long time already for Linux. And I mean, GPIO was a topic last year because prior to that we had been using sysfs, and before that there was nothing. And then of course Industrial I/O came out a while back still, and it gave us access to a bunch of different things like accelerometers, PWMs, all sorts of things. So I'm sure that a lot of people saw these APIs in their infancy and have watched them mature over time. So it's kind of like, you know, you're seeing your kids grow up, sort of thing. So there's one thing that all of the previous devices in this previous slide have in common, and that is that they are full of what we refer to as non-discoverable buses, or devices on non-discoverable buses. And this is a definition that I did not retrieve from anywhere. I just kind of drew it out of thin air. But so there's this dichotomy here. What's a discoverable bus? What is a non-discoverable bus? A discoverable bus is something where you can probe devices attached to the bus, and you should be able to get some useful information back to sort of build your your database of what you're connected to. And ideally, these responses to your probe would contain useful information, such as categories that the device belongs to, or sort of standard. And I guess it's only necessary if you want to be useful to the rest of the world. But number three, if you use a standard protocol for your device, then it's useful to everybody else. So as an example, PCIe, USB, Ethernet are discoverable. There are various levels of discoverability there. And then, of course, things like GPIO, I2C, and SPI are non-discoverable. Now, that means it doesn't mean that you can't probe for things on the bus, but just that there's not a standard way to do so. So there's a tool, for example, called I2C detect, which captures a lot of EEPROMs, a lot of sensors, but not every single one. And that's because the I2C registry layout was never standardized. So it's been a bit of a wild west there. And let's see what we have. So I'm going to take a small aside. And the reason that I personally find this concept of discoverability really important is because around the time when Project Ara surfaced, which, if anyone's unfamiliar with it, it's the it was basically the modular phone. It was started by Motorola's Advanced Technologies and Projects division. They were acquired by Google. There's a lot of former DARPA employees, and they created this phone where you could take, you know, the camera or a battery. You could upgrade the processor. They basically provided an exoskeleton with slots to fill with different hardware, and then all of the different modules would speak a common protocol. Let's see what I've got next. Yeah, so of course modules could use whatever buses, whatever devices, whatever technologies they needed to use in order to perform their function. So for example, you know, a GPIO would be perfectly fine for triggering the flash on your camera, but of course you also need a video interface to that, which is of course MIPI. And actually, MIPI was one of the partners in this venture. And oddly enough, Nokia actually put a lot of the initial research into Unipro. So as I was going to say, a long time ago, I had this great idea to create a cool little dongle that would expose all of the non-discoverable buses that embedded engineers are familiar with, but it would do so in such a way so that it made them discoverable. So for example, you can get a USB to serial chip, FTDI. FTDI gives you the ability to pull GPIO, gives you the ability to write GPIO, and of course it functions as a UART, but there's no way to get an interrupt from those GPIOs, so you're forced into polling. At the time, I thought it would be really cool to actually come up with a device that gave you the ability to get an interrupt from a GPIO or function as any other device out there. And of course, there were products out there like the Bus Pirate that did that, But of course, the Bus Pirate just had its own protocol that worked over serial. It didn't give you that familiar Unix device model that really, I think a lot of us wanted to reuse. In any case, what Project Ara did was make all of those non-discoverable buses discoverable. And that was a really big thing for me. Now that works with modules and that sort of thing, but it might not work so well on your traditional desktop computer. In any case, I thought it was quite interesting. And when I started this concept of the IoT microconference, I proposed my original protocol, which I called Disco Ball, Discoverable Buses for All. I proposed that to Greg Crow-Hartman, and I proposed that to Linus Valej, and I proposed that to Jason Kreidner, of course, and they're all like, no, 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 no. Use this Graybus thing that we've already integrated in the kernel. I'm like, I remember reading about Graybus. So that's how that happened. And of course, now we're going to get into Graybus. So Graybus is the application layer that runs on top of the Unipro network for Project Ara. And it sort of organizes entities as shown in this diagram here. So every module has one or more interfaces. Every interface has one or more bundles and an optional control C port. And then, of course, every bundle has one or more C ports. So the control C port is, they say it's optional, although I think it's quite important to the whole protocol, to be honest, because that's where you get the Graybus manifest from and that sort of thing. In any case, every C port that exists within a particular bundle has to be related. So, for example, if we used bundle 1 here as a GPIO bundle, then all of the C ports that exist in this bundle would be GPIO. Similarly, if this one was I2C, then those would all be I2C C ports. Let's see what's next. So the way that Graybus ties this all together, as I mentioned, is the Graybus manifest. And this is an actual manifest that I put together. This is actually a decompiled manifest. So I took it from the binary format. And let's just go over what's here. Of course, we've got, I should mention too, a single interface must have a single Graybus manifest. That's not always obvious to everybody. You can have multiple interfaces on one hardware module, but each interface should have its own manifest to tell you what's attached to that interface. So in this case, our manifest, we've got an interface descriptor with a vendor string and a product string. And if you search around in here, then you'll see that this one is Zephyr Project RTOS as the vendor string. I don't know if I have the official capacity to say that. It was for my demo application. And then, of course, you have the product string, which is Graybus service sample application. And then we've got the control port, which is class 0. So that's the C port protocol, I believe. Oh, no, sorry, that's the bundle. So the bundle class is class 0 for the control bundle. And the C port protocol is number 0 for the C port, control C port. And then, of course, you've got 0XA, which is a bridged PHY bundle descriptor. And that one, if you look around, is for the GPIO C port, which uses the GPIO protocol. Similarly, for bundles 2 and 3, you've got I2C and SPI. A couple of special entities that exist within Graybus are the application processor and the supervisory controller. So the primary purpose of the application processor, and I should mention in this case, oh, it says right there, it's inside the Linux kernel. It communicates with Unipro over the AP bridge, and it is really the brains of the whole Unipro/Graybus network. And then the supervisory controller is really just there to notify the application processor. when a new module is inserted or when an existing module is removed. And then, of course, just to, I think it handles power as well and a couple of other things. So that's it for Graybus special entities. Now, a few years ago at ELCE, a nice fellow named Alexander Bayon from Bay Libre came up with this idea of reusing the Graybus work that had already gone into the Linux kernel for IoT. And if you think about it, if you look back to our previous slides with all the smart home devices, it makes a lot of sense. The Graybus protocol can handle fairly trivial interactions like turning a light off and on, or reading the state of a switch, or probably well, I mean, you can listen to audio, you can stream audio, you can stream video, or there are a bunch of different things. And of course, those are all things that exist in our smart home currently. So, of course, it made sense to reuse it. There are some corner cases where it doesn't handle things, like if you're doing a control panel, that control panel might want to speak directly to the device that it's controlling. If you can see my hands. Otherwise, I guess you'd be looking at possibly backing that through a server of some kind, like somewhere on the internet in the cloud. In any case, Alexander was the right place to start for the work that I've been doing with beagleboard.org. I should mention that, of course. All of this work that I've been doing is driven by beagleboard.org. And he came to speak at Plumbers last year, which was our very first IoT micro conference. Now, Alexander contributed a couple of really important things. One is gbridge, which is a user space program that interacts with the Linux kernel. gbridge implements the SVC in software. And also, I guess it communicates with the Linux kernel over netlink. So there's a second piece of technology involved there, and that was a kernel module called gbnetlink. We've got some links here. You feel free to check those out at some point. So the original, just to reiterate, the original topology, I borrowed this from Alexander's slides. I hope he doesn't matter, or I hope he doesn't mind, was that everything communicated over this UniPro switch. But of course, when you're just dealing with various topologies that gbridge supports, you would probably prefer to use this approach. So, and just to clarify, gbridge supported, when it was released, it supported, I think, 3 different transports. One was UART. Let me see if I actually have a slide there for that. So yeah, okay, here we go. So the host controllers, as they're called. From the gbridge perspective, there is the UART, the C port ID, which is a critical piece of information in all Graybus messages. That was actually just kind of bit stuffed into one of the reserved areas in the Graybus message header. BLE, I believe, using, and I didn't try and reproduce this, but he was using, I believe, a GAT profile. And then, of course, gbsim, which, if any of you are familiar with this, involved using a BeagleBone Black. It was actually the Project R reference platform for a lot of stuff. And of course, Jason Kreider was quite heavily involved with that. And I believe also Vaishnav, who presented first today, was involved in that. And then lastly, we have TCP/IP. Alexander originally designed us to use MDNS, also called Bonjour, 0com for Avahi, I believe, to discover neighbors. And then gbridge would just announce that to the Linux kernel via netlink to, I guess, with the gbnetlink module as an intermediary. And then, yeah, that's how gbridge worked. The one, I guess I should mention, one of the quirks, one of the kind of assumptions here with gbridge was that all of the C ports for a device needed to be sequential TCP ports. So if an MDNS host was advertising a service, it typically advertised that service as C port 0, meaning the control port. And then if you wanted to do your GPIO C port on the next available C port, that would actually be, so for example, control in my demos I use is 4242, which is the traditional Zephyr TCP IP port. If you were to have, if that was our control port, then the next available TCP IP port, which would be 4243, would then be GPIO or I2C or SPI. So that was just one of the kind of quirks that it had. That's something we might want to change in the future. In any case, having some background in 802.11, sorry, 802.15.4, and BLE, and knowing that BLE was just supported, it just gained support with 6LoWPAN in the Linux kernel and in Zephyr. It made sense to me from the low-hanging fruit perspective to just use TCP/IP for this, because all Graybus needs is a reliable transport. That's not to say that there are not better protocols out there, but and I'm sure there are, but the idea was just to keep it short and simple. I just wanted to get from A to B with as little fuss as possible. Yeah, so we've got a number of people that have smart devices in their home, no surprise. I was actually using my Google Home to tell me when to cue the time is up cards. And speaking of which, is anybody moderating my talk? I should just ask that. Jason or Drew? So I think I've got quite a bit of time left.
Oh, I figured you were good self-moderating. So if you need some, if you want me to watch the clock for you, I'm very happy to do that. I'm mostly just taking it in and making some comments in the chat. Just the GBSim was actually done by our friends at Consulco, like Matt Porter and the like, so that were under contract for Project Ara.
That's right. Is Matt?
So did you need? I don't think so. I don't see Alexander either. So hopefully they'll catch up on the stream and chat with us later. But some moderation wise,
hack to use for a couple of weeks. GBSim was.
Yeah.
Well, it's pretty cool, and we've had some fun use of it, and it helped us kind of architect some things out moving forward. So thanks for doing it, Rob.
I don't think I've ever met Rob in person, but yeah, so I guess Rob, you're part of Project Ara then, right?
Yes, I was.
Okay, so you're going to call me out if I make any incorrect assumptions here, right?
Well, the phone you showed worked with the car battery. I can say that.
Yeah, I was going to say, I don't want to speculate why Ara was shelved, but you know, I had some guesses. Okay, so continuing on, and if anybody has any questions, please feel free to interrupt at any point. Jason, do you have a question?
No, just I want to know what sort of moderation you need. If you're wanting me to jump in with questions or help, you know, with folks that way, just let me know. Otherwise, I can leave it to you to continue moderating.
Yeah, just let me know if I'm starting to run over time or if I have 5 minutes or something like that. That'd be great.
Okay, I'll try to do the 5-minute warning.
All right, so just continuing on here. Okay, so that brings me to my next topic, which is Zephyr. I had done an eval of various RTOSs out there, and I knew that I wanted to use 6LoWPAN, obviously. I wanted to keep things in the TCP/IP realm, just for now at least, but for sure at least within the IP realm, just because it made things a lot simpler. And out of all the various RTOSs I evaluated, the one that had the fewest incompatibilities with Linux in terms of IPv6 and in 6LoWPAN and various quirks was for sure Zephyr by a long shot. Now I could do, I'm sure Kate would love to hear this, by the way. I could do a talk on Zephyr alone. I love it. I've been using it for a while and contributed in a few different areas. It's got a lot of features. The community is fantastic, and they've set up their repo on GitHub, The documentation is incredible. Yeah, so as I said, you can use the BSD sockets API right out of the box. Oh, Kate's there. Did you have a comment?
Just thank you. And make sure to pass the comments on to Zep, the community.
For sure. I invited a bunch of people to come and participate in this micro conference as well, because I don't think it would have been possible without them, to be honest. So BSD sockets work out of the box. It's got every networking protocol, more than most people are even aware exist. 6LoWPAN support works perfectly, and IP over virtually everything. We've got UART, it does SLIP, it does PPP, you've got IP over CAN, you've got 802.15.4, you've got Bluetooth Low Energy. What else? I'm probably missing something right now. Let's see. Yeah, so literally it is the IoT operating system of my choice in any case, and that's why we chose it for this project. It supports POSIX threads. There's a little bit of work to do. I'll mention that later. Device tree, so one hardware configuration mechanism and one software configuration mechanism that is familiar to most embedded Linux kernel developers, or Linux developers, I should say, which is kconfig, and I'm sure a lot of people use menuconfig or possibly even xconfig. It's got a shell. Yeah, documentation, community, everything. I'm blown away. And I've been involved with it from microkernel facilities like, let's see, I did socket pair, which is pretty trivial. It was quite well tested. Currently, I'm adding pthread support for automatically allocated POSIX thread stacks. I went down a bit of a rabbit hole after last year's Linux Plumbers and started implementing the Bluetooth Low Energy Split Stack API implementation for the CC1352R. That is still not done. It is quite complex, but I had a lot of help from TI and a lot of help from actually the Zephyr community. So I wanted to say shout out to Viniac for that. In any case, so yeah, here's an example of the Zephyr menu config. It's quite familiar, as I said. You can scroll through everything. You can look up what dependencies exist. So yeah, quite familiar. The one thing where Zephyr might come as a slight surprise to people coming from the Linux community is how it deals with device tree. So as I said, device tree is the single, at least the philosophy right now, I think it's almost 100% realized at this point. But the philosophy in Zephyr is to have a single point of configuration for all pieces of hardware. That can come from several sources, because you have the SOC device tree source, you have a bunch of device tree includes, you have the board device tree source, some additional includes there, and then you've got application-specific device tree overlay files too. So what Zephyr does is it pulls in all of these pieces of information, and it forms a collection of all of them, and then it pre-processes the device tree source to provide you with a compiled and generated C header file. Now, why that is actually quite good is because when you put all the config, I mean, I've worked at companies where everything is configured using a C header file, and it can get just insane. The complexities, when you don't have a tool to analyze your dependencies and to provide errors for you when you're misconfiguring things, it gets a little bit insane. So I've suggested in a number of places where we're using, for sure, embedded systems, bare metal, is to use device tree for that specific reason, because it was an IEEE candidate technology. Even with the ARM ecosystem, with the EBBR specification, device tree is an option. They, of course, prefer ACPI, or ACP, as some people say, and the SBBR and EBBR, if it can be done. But yes, it's a way to collect all of that non-discoverable bus information in a single place. And up until Graybus, it was, well, one of two options, really. The third option being just C macro chaos, right? So moving on, let me, I guess I should say too, the thing that makes Zephyr's implementation of device tree for configuration so appealing is that configured, I guess, hardware configuration, device tree configuration primitives, they only occupy ROM footprints when they're actually used in the compiled artifact. So one of Zephyr's philosophies is to always fit into, I believe it was 4K or something like that. Like the hello world should not, surpass more than 4K. I'm not sure if it still is the case, but definitely every byte matters, and we have to squeeze into some very tight parking spaces. So for that ability, just to pull in only the parts that are configured is quite important. There is a drawback. You cannot parse the device tree binary at runtime because there is no device tree binary. It's just baked into your application and the kernel as compiles on constant information in the .text section or the .ro data section. So that brings me to my next task with the project that I was involved in with BeagleBoard was to get Graybus working in Zephyr. And actually, you know what? Let me do another poll here because, 8K. Thanks, Kate. Kate just reminded me that it's actually 8K now for Zephyr. So if people were at Zephyr, at the Linux Plumbers conference last year and attended the IoT Micro conference, it'd be nice to see a show of hands. So we've got a poll going for that. Let me know, if you're in attendance, and because it would be nice to know if our community is growing. Jason, do you have a question?
Just letting you know, 10 minutes left, or actually 9 minutes now.
Oh my gosh, okay, thanks. Good job. Okay, so the original nut export of Graybus was actually quite straightforward to use. I believe the only thing I needed to add was a couple of sleep routines because it was using uni-standard sleep routines, QSort, oddly, and the Atomics API was slightly different. Of course, they use a slightly different linked list implementation as well, but overall the porting effort was quite straightforward. And if you happen to hang out in the hack room at last year's Linux Plumbers conference, you would have seen me demonstrating Blinky on this board, which was Rev A of the Leash PCB from beagleboard.org. We've actually renamed it now to Beagle Connect, and Jason has a repo up there. I think we're on Rev C currently. The not so great thing about this demo was that it was UART only, so it didn't make use of the radio, and it hard-coded a lot of things, including the Graybus manifest. So yeah, as I mentioned, device tree is quite entwined in the Zephyr build process. So yeah, here I've just got basically what I already spoke about. So I'm going to continue here. Feel free to ask questions if you have any. Yeah, so inside your device source file, where you're writing your device driver for GPIO, like a chip-specific GPIO or anything like that, you'll be using this kind of format where you define what device tree node or label you're dealing with. You include the device tree header, and then you call this macro, which actually iterates over each instance of your device. And from there, you're free to declare a few things. I mean, first of all, you need an init function. In Zephyr, there's a a const, compile time const config structure that you can define if you want. In the macro, these are all just custom void pointers. And of course, a custom data section, and then an API. So yeah, everything except the init function is actually optional, so that's quite flexible. So I needed to kind of come to a conclusion about how I was going to integrate this. So one option was to require users to maintain their own Graybus manifest and to maintain a device tree file for their application on the board. It seemed like a lot of work. So my alternative was to generate that at compile time. Now, unfortunately, the Graybus manifest has enough information for Graybus to work, but not enough information to communicate what resources the platform has and translate that into the Graybus manifest. So it wasn't really feasible, in my opinion, to use the Graybus manifest to generate a device tree. I could be proven wrong about that. I happen to go in the opposite direction, and rather than write a bunch of board init files and have a bunch of random startup functions, I decided to use device tree to generate the Graybus manifest. Ideally, this would be done at compile time, but right now it's not at runtime. Sorry, I'm actually running behind on my slides, so I'm going to try and scoot ahead. So here we've got, so I came up with a plan. I devised a plan for how to declare Graybus within Zephyr. You've got a Graybus top-level entity, and then of course you've got your string identifiers underneath that and your interface. I've actually declared the interface as second layer and bundles as second layer as well, and I've used a p handle to refer to the interface. But technically speaking, it should also be possible to nest the bundles inside of the interface. Of course, control bundle 0 is reserved. So yeah, here we've got a nice word C controller, pretty straightforward. And as you can see here, we actually refer to a physical device. Same with SPI. SPI refers to the physical unit. And of course, we provide a bunch of extra metadata, meta information for that Graybus manifest that otherwise would not be feasible if we went the other way around. Additionally, we declare what SPI devices, or what the capabilities of our SPI bus is and how many chip selects we have available. So this is sort of a work in progress, and I'd be really happy to take some pointers on that. But over here, I should just say that we implemented GPIO, I2C, and a SPI fake device, and that enabled us to prove out everything in Zephyr's really incredible test framework. So that was quite useful, and I think we've got pull requests up for that. Thank you.
Stefan beat me to it on the 3. If you want to, I don't know if you're going to do a demo, and I don't know how sharp they're going to end our time. Yeah, it's 3 minutes.
Okay.
So you're good to keep going and relax and just have a good discussion.
All right. So thank you. So the last thing is just to polish this a lot, because we want to generate the Graybus manifest. We want to leverage device tree to generate all of our instances and to incrementally put that manifest together. I thought, why not go the extra mile and automatically register these virtual Graybus devices with a Graybus service. So now that's done for you purely declaratively. So if you add your device tree information there for Graybus, the service will start automatically, assuming you've got the services set selected in kconfig, and it's just that easy. So yeah, okay, so a couple of items to do with Linux. Actually, Stefan kind of mentioned a couple of things that I have in this slide as well, so it'll give me a chance to skip over some things and shorten up the talk. So the fundamental philosophy with Graybus is to keep the intelligence on the host. We don't want to have drivers buried in microcontroller firmware or wireless microcontroller firmware that never gets updated, never sees a security update. And as I said, that covers most of the use cases where you're using a one machine to adjust the state of another machine, like turning on a light or adjusting your thermostat and so on. So that means we can, and Vaishnav as well today gave examples of a bunch of drivers that worked almost with very little modification right out of the box. And of course, he had made a couple of additions for Microbus on top of the Graybus specification. Now that doesn't preclude us from using other community board standards as well, like the Feather, and also yeah, and sharing some information between them. Personally, I think that Graybus would be a really good candidate to move into a Linux Foundation project. So here's the proposal. I don't really want to skip back to Alexander's topology for how gbridge is implemented and how it handles the various entities. Just a second. Okay, Google, cancel the alarm. That was for me. We would like to, since we're basically using socket file descriptors, we would like to move the SVC from gbridge inside the kernel. And then gbridge itself would probably just be responsible for authentication and setting up that session key for encryption. Inside of the Linux kernel, it's fully capable of using cryptographic engines and that sort of thing. But there is a fair amount of work to be, some research to be done, and it would be nice to see what, for example, the thread working group has done there as well. Yeah. And then, of course, WPN USB, which Stefan already mentioned. And luckily, we found Michael. Michael did a great presentation today, too. And I'm really looking forward to getting, oh, sorry, typo here. This should say 802.15.4, not 802.11, honestly. Yeah, so I'd like to get, I think we'll probably have something working for WPN USB within a couple of weeks, because BeagleBoard is working on that, and I think Stefan might be interested in contributing, and also the Riot developers, Kuhn, wanted to take part in that as well. So yeah, I've got just a couple of slides left, and I wanted to mention open problems. So yeah, Graybus, no authentication that's standardized. It would be nice to have a couple of supported mechanisms. We have public key, that's what, we have a proof of concept for public key authentication, and using that asymmetric encryption to set up asymmetric encryption using just standard AES 128, mainly because most of the wireless SoCs out there already have a hardware block to do AES 128 encryption. Again, I would like to look at commissioning, joining, and rejoining, see what examples are out there, and possibly use what other people have done already, like Thread. Jason, I guess I'm out of time.
No, it's not that, because I think Kate said that we could run a bit over. You are a couple minutes over, but I think that's fine. I was going to try to suggest that you talk about what's working today, because I know you'd sent ahead of time some information, and I thought you were going to demo today, because I think the fact that you have I2C now working over Graybus with Zephyr and using gbridge, right? I think that whole stack of what's actually up and running today. So there's definitely these open problems, but I mean, you've got a lot working pretty, now.
That's a good point. I don't want to focus on the negative. I just wanted to highlight what work is still to be done. I'll let people to refer to this on their own. It really touches everything. Zephyr, the Linux kernel, Linux user space. There's quite a bit of work to be done, and we're actually at the point now where we would really like community help. So Linux side of things, here's an example. I would have been able to do a demo today, but it didn't seem like I would have been able to get this last bit of work here done to get the ambient light sensor to pick things up. So I think this is the slide that everybody was asking for. Got a bunch of video demos. I mean, they're all just basically blinking LEDs. So let's see if I can just copy this link. But I wanted to just illustrate that, yes, we do have, how do I close the poll? I'll close it later.
Finish presenting. Can you enable your slides for download?
Yes, yes, of course.
I want to go click some links as opposed to type them.
Nice.
Went to the Plumbers site and tried to copy and paste my link. Okay, all right. Looks like I have to open the link first and then copy and paste.
They're in the. I just pasted the link in the chat if people want to click on the PDF. It's also in the shared notes.
Perfect. Okay.
Yeah, and it's nice to point out that even though there's upcoming hardware, like the Leash PCB, that the launch pad and the sensor tag, along with the AT-USB, kind of makes all this something that people can run today.
For sure, yeah. So this is a demonstration that we have running over 802.15.4. I'll just loop that back because it was really quick. This is the launch pad right there. And as you can see, it's actually streaming pretty fast. The LED is unfortunately not super bright there. Let me, another video. Actually, it's not doing great at the moment. There we go. Another one. So I just wanted to also demonstrate that, you know, as expected, it's working over BLE just as well. I don't know if you can see the LED in that video. But yeah, this is the NRF 8420, I believe, design kit. So yeah, we've got 802.15.4, we've got Bluetooth. I know what that's like. Yeah, we'll have to have the kids in the video at some point. Yeah, so we've got multiple transports. We've got 15.4, we've got Bluetooth Low Energy, Wi-Fi, of course, Ethernet, SLIP, point-to-point protocol over UART. In theory, it would work over the CAN bus, but I have not tested that. So just because of the way that Zephyr's set up, when you're talking IP, it's pretty straightforward to do anything you want to do. So yeah, and I guess there's one more here, which was a couple of weeks ago. I remember Jason was pretty thrilled when I demonstrated this. So this is the, just waiting for my internet again. Resolve this link.
That was why I started to take myself on mute, because I wanted you to show this one.
This is taking a while. Oh, there we go. Okay, so yeah, this is the Texas Instruments CC1352R sensor tag. And we've got RGB discrete LEDs here. What you don't see, unfortunately, is I added it to the script later, but we're actually peeking into I2C registers. We've got a ambient light sensor on the I2C bus, and we've also got a temperature and humidity sensor on the I2C bus. Now, of course, you can test these drivers on the Zephyr device itself, but you don't even need to. Strictly speaking, you could use the opt 3001 driver in the Linux kernel and just say, this is the I2C bus that I'm dealing with, and that would be, in fact, your Graybus I2C device. So yeah, I just wanted to put up a couple links here. We've got GitHub gists. The first two are a little bit deprecated because they were done before I added the Graybus system service to Zephyr. This last one here is kind of, you know, the thing we're gunning for, which is, you know, it just kind of works out of the box after you declare your device tree setup in device tree. So yeah, that's the current state of everything, I guess, in our project. And I wanted to leave a couple of links here. My development branch is the Graybus service LPC 2020 here. That's going to stay up there forever, you know. And then, yeah, we've got the sensor tag there. We've got all of the fake I2C devices. So if you want to add a fake PWM device and come up with a Zephyr API for that, you know, make a pull request. Zephyr is looking for that kind of stuff, generic API that can be used across multiple vendor boards. And that's really what we want. We don't want to, I mean, as much as we love vendors, we don't want to have to rewrite things over and over again using different vendor SDKs. We want to have a consistent device interface. So of course, the Zephyr Getting Started guide is down here, and they've got a great Slack full of lots of community support. And of course, the Beagle Connect project, which is in Jason's personal repo there. So let's see. I think I'm basically done. yeah, so now is the time to start contributing. We're looking for help. We would love it if people could get involved, get active in the communities. You know, if it's Zephyr Linux user space, even cloud, like we're at the cusp where we're going to be needing cloud developers right away. So this is coming down the pipes. And of course, we've got the Beagle Connect. The Beagle Connect with the new WPAN USB driver that is underway. That's going to allow, I guess, you know, different chipsets to work with the same 802.15.4 interface or just over USB. So just plug it in and it works, just like the AT USB does nowadays. Thank you, open source hardware. I think it was trying to remember the guy that created the AT USB, but I can't off the top of my head. Wolfgang? No. In any case, yeah, even Graybus.
It's Werner. Werner Almesberger.
That's right, Werner. So yeah, thank you, Werner, for the open source hardware. And actually, the AT-USB device that I had two. One of them I gave to the other BeagleBoard developer, Eric, who's down in Arizona. And I said, this is, you know, I hand assembled these with my buddy Mike. And it's going back a few years, so please, you know, treat them with care. So I'm looking forward to another round of open source hardware, and especially the Beagle Connect, that enables us to develop our IoT applications. So that's it for me. We've got Q&A. I'm going to come back to this. So I just want to say thank you. Thank you to beagleboard.org. Thanks to Jason, Christy. Thanks to Drew. We have a really great electrical guy, Chris Gamble. I'm sure everybody's heard of him. Eric Larson. Everybody from Texas Instruments, Mark Grozen, incredibly helpful. Everybody from the Zephyr community, Viniak, Andrew Boy. There's too many names. Peter Abigo. Really, it's just been a pleasure working with this community. So I just wanted to say thank you. And yeah, I guess let's open up Q&A if we still have time, if everybody's still awake. And then right after that, let's do a group photo. So yes, please throw the questions at me. Complaints, questions, anything. I know Rob probably has some questions if he's still around. I'll check out what's in the chat as well.
Well, I'd be happy to talk about the dynamic aspects that was brought up in the chat. Maybe we do that after. I don't know.
Yes, sorry about that. I just got a phone call. I might have missed your question, Rob.
No, I was just saying I'd be happy to talk about the dynamic aspect of that came up in the chat, but maybe do that after Q&A.
Yeah, I don't know if it's going to go here in the session, or if we should probably just move that over to the chat. I think Frank Roward would be really important to have in that discussion as well, because he's been working on device tree sockets. I don't know if he's made that public or where he's going with that, but I know he was reviewing the Microbus patch, but generally just talking about dynamic buses for making these buses dynamically instantiable is going to be like an immediate follow-up discussion right here. So
I think that's a great idea. Let's check that into the chat because I have tons of ideas. So any other questions? All right, I'm going to say going once, going twice. Anybody? Okay. Oh, so for all the presenters, thank you today and all the organizers, Jason and Drew. I just want to say thanks. And if you could get all of our faces on the same screen for a group photo, that would be really cool. So Michael, Gilda, Michael Magyar.
Yeah. I was going to say, do any of us want to jump in a break room or a hack room, or are we just going to use text chat?
Rocket chat or whatever?
Well, there's the text chat, yeah, which I'll paste the link in, but we can also jump into a hack room, which is video like this, which there's no like time limit on using.
Okay, yeah, that's a good idea. Let's do our group photo first, I guess.
Yeah, yeah.
So we're missing Vaishnav. I guess Vaishnav is asleep already. I don't know.
It's pretty late for Vaishnav. And Michael. There's Michael. Great.
And Michael Gilda. Let's see if I can. I don't know if he's still
Is there
here.
a way to minimize your slides so we get more space?
Yeah, for sure. Okay.
Presenting, and then you'll be able to take over the full thing.
Okay. Michael Gilda, Vaishnav. I don't know if Vaishnav is still in.
He's in chat.
Sleep.
Yeah, he might be.
A little bit of background noise from you, Jason, so I'm muting you, okay?
That's fine.
Anyone else? I don't know if Vaishnav has his camera hooked up for what's going on. Michael Gilda. Yeah, I'll send him a quick message as well. Okay, give another few seconds, and if we haven't seen any others, I think I'll just. Oh, we lost Jason now. Okay.
Oh, his camera's on. He's just coming back. To the background.
All right, let's do it. Select area to grab. Everybody smile. All right. Okay, that's it. And I guess that would conclude the IoT Micro Conference for this year. And thanks to everybody for participating and engaging. Yeah. Okay. Yeah, I guess that's it. And I'm not sure if I should hand it off to anybody or just.
I think at this point, I'll tell them to, they can stop recording now.
Okay, thanks a lot, Kate.
Good thing.
Take care.
Okay, thanks again for a good MegaConf, guys. Take care.
I need to save the notes.
Yep, please do. Save the notes, save the chat, just so you have the references.
Well, so Kate, are we? I put my BOF on the conference page for it, but for the micro conferences, should I chop it up and put each one on each talk, or how are we doing that?
Yeah, I think the recordings will be available as a full stream tomorrow, and then
Okay.
over time processed. And if you're willing to help with the processing of chopping it up to specifics, I suspect that people welcome the help. So I'm happy to volunteer you for this one if you'd like to help with it.
Yeah, I didn't know what the best place was to do with the text document. So it'll be accessible.
Yeah, probably put it up with the mini conf along with the slides and everything else.
Is there I see the pages for the individual talks in our micro conference, but is there a page for the micro conference itself with attachments?
Yeah, I think there is. Just a second, see if I can find it for you, okay? Yeah, here it is. Let's see if they let. And there's presentation materials that can be linked to it too. So it's in the chat right now.
Okay. Cool. Okay. So I'll attach it there.
Yep.
Okay. Awesome. Thank you.
Thank you. Good
Yeah.
microconference. I enjoyed listening today.
Yeah.
Take
We
care.
had some good Zephyr content this time.
Yeah, that's also a bonus as far as I was concerned. So like you say, I'm happy to be on this one. Take
Awesome.
care.
Cool. Thanks.
Sure. you.